Welcome to another coding session where I create a new programming language called Plum. It's on GitHub. It kind of looks like this. I won't go into too much detail of the language right now. If you want to know more about the language, just watch some previous videos. So, today I want to implement closures for this language. And what do I mean by closures? Let's maybe first look at an example in another language. For example, Rust. So, in Rust, you can create functions. Let's just get something running. Hello. And maybe compile like Rust C, I think. Does that work? Yeah. Okay. So in Rust you can define functions like these. And the order doesn't matter, unlike in C++. So for example, even though foo is defined down here, we can still call foo up here. So functions are these top level things, and functions can reference functions that were defined before and that were defined later on. Yeah. In contrast to that, closures are basically functions as values. So, for example, you can say, I want to create, some function bar, let's say, and they have different syntax. So in Rust, they have these pipes, and you can put arguments in between. So for example, a function that takes a U8 and returns an X. I think it looks like this. Maybe they have to be parentheses or that. Nope. Okay. Yeah, but then we can basically call bar with 5, for example. And let's maybe also print that. That's the result. And right. Yeah. Let's maybe do something like x plus x. Yeah, result 10. So closures, they have a different syntax, first of all. But also they can be defined inside of functions, and they are really values that can be passed around. Which also means that because they are defined inside of functions, they can't reference other closures which are defined later on. So, for example, you can't do this. That should not compile, yeah, because buzz doesn't exist here. To fix that, the order really matters. So you have to switch them around and then things work. The cool thing about closures is, though, that they can also capture variables from the outer scope. So let's say we have some, variable a. And here we can also say we take x plus a. And that is fine, being able to say, okay, I want that plus that. That seems intuitive. But it gets kind of hairy when, for example, let's say we return this function. So here we return best. And I know it can be simplified. That means that this entire function now returns a closure. This closure right here. Yeah, let's maybe even give that a nice name. So now let's say we have some sort of, make incrementer. It takes an a, which is, let's say, usize, and it returns a closure that takes some x, and then returns x plus a. And then here we can say, a is an incrementer of 2. And then we can call a of 3, and we should get back 5. And this doesn't work because the question is, what does this function return? It returns something like another function. But it turns out in Rust, functions and closures are actually different types. Functions, these top-level functions here, they can be represented as a single function pointer. Because when we compile our Rust program, basically we'll end up with some machine code that corresponds to this function and some other part of the binary that contains machine code instructions that correspond to the main function. So if we want to pass around a pointer to main, for example, we can just literally pass around a pointer that points to the address, where main begins. For closures, though, it's kind of difficult, because closures, as we see here, they can capture variables. This closure captures this A. Let's maybe also capture some sort of B here, because why not? And this B, it goes out of scope at the end of the function. But it should still live on because the closure depends on that. And this is not some global B that can just be baked into some address, because for different invocations of make incrementer, the A, for example, will be different, and the B, if it depends on A, it could also be different. Which means we need to keep around these values, these captured variables is what they're called, variables that are not inputs to the closure, but that are from the surrounding environment, A and B. These captured variables need to be kept around and basically be passed around with the function itself. So let's maybe do that, what Rust suggests here. Basically saying, hey, this returns this. And this is the syntax for a closure. Again, this is not super important right now. Basically, what it tells us is that this is a function that takes an integer, like a usize, and it returns a usize. Yeah. Okay. Yeah. Another thing. So this function here references A from the outer scope. And yeah, we need to, for now A is just, a number, but let's assume this is some really complicated data structure. In Rust, the compiler has to know when things are freed. So when this huge data structure here is used inside of the closure, we can't just say, well, now we're going to free it at the end of the function, like this. We can't do that. Because then when the closure is returned, the A will no longer be valid. Which means only when the closure itself is destroyed, we also want to destroy all of the captured variables here, the A and the B. And we can say that by saying this move in front, which basically tells, hey, please move all of the referenced variables into this closure, which means the closure now owns them. This returned closure here owns them. And which means when this A goes out of scope, that's when the 2 will be freed and when the 3 will be freed. Now hang on. That's when the 2 will be freed and when this 2 right here will be freed. Yeah, this works. Now the question is, how does this work? How do you bundle up these captured variables and the closure, the function into some sort of value that you can then call later on. And to understand that, let's write the same code without closures, with only top-level functions. That would mean that we can't write something like this. So let's instead write a top-level function. A function, I don't know, incrementer code, takes an x and it returns another usize. Well, it returns x plus a plus b. And again, here this won't compile because we don't have access to any a and b here. And then here, instead of like doing this magic Rust thing and letting the Rust compiler create a closure, we're just gonna return the function. So incrementer code. Actually, let's for now just comment this out. Which means that we can call make incrementer of 2 and then call that with 3. Yeah. You'll see that the return type is still something that basically can be called, is what this says. But we can be even more strict. So let's maybe let the analyzer figure that out. We can say this returns this. And this is a different syntax, which tells us, this is a function pointer. It's just a pointer that points to exactly the machine code of this function. Yeah, that works. Yeah. Now the question is, what do we do with these local variables like a and b? The incrementer code needs to be able to access them. Basically, as soon as we create a closure, we also need to associate these values with that function pointer. So we're going to let's create a struct incrementer. Or let's say closure. Closure. It contains the captured variables like a and b, and it contains a reference to this function. And then this can just return a closure. By saving the a and b in here. Oh yeah, this is a closure, and then when we call that, we can't use the fancy Rust syntax here, but we have to actually say a dot function, I think, with these values. Yeah, now we have these values, and the incrementer code, it doesn't just accept the x, it can also accept the captured variables. Like this, a dot b, and 3. Yeah, and this doesn't work because, this is no longer a function that takes a single int, but it actually takes 3 ints. Yeah, and this works. Right. So when you create a closure in Rust, this is what actually happens, And it's even a bit more complicated than that, because we could have multiple closures with the same signature. So for example, the closure from int to int. And for example, we could say this right here is, again, I'm just inventing syntax here, Closure from int to int, or rather usize to usize, is, I don't know, if some condition, then make incrementer, else make something else of something. And this could create a closure that is, has the same signature, and we should be able to call that in the same way, but it may have a completely different structure, a different function pointer, like a different function that corresponds to that code, but also like different captured variables. And that means that this approach doesn't work. We can't just say this is, this is a closure, because this closure, they will have different memory layouts. Here we have a usize and another usize. The other closure may capture 5 things, for example. So the types of these won't be compatible, even though we will basically use them the same way. Yeah, so how do we deal with that? The way it's usually done is by having some generic int closure. And instead of saving the captured variables directly in here, we save a pointer. Let's say pointer. Oh, I'm not entirely sure how pointers work in Rust, to be honest. Not like this. Probably not like this. Should have done this in C or something, because I could do this in C. Yeah, let's do this in C, which is even more interesting, I think, because C doesn't have closures. So we'll really see how that allows us to do something that we couldn't do before. Okay, yeah, converting this to C. So this will be a void main, and instead of print line, we will have print f. And instead of this, we'll have, closure, like some struct int. And let's just get the thing working that was there before, with an int a, int b, and a function pointer. So let's just say a pointer to a function. Yeah. And again, I'm not sure how function pointers look in C. What? They look horrible. Okay, I guess that's fair. What? That is. Okay, I guess. So this will be a function that takes 3 ints and returns an int. And yeah, and here we can just do called make incrementer. This will be a, and then in here we can say a dot function. Yeah, and by the way, this is a closure. Called make incrementer, and that should work because we put these functions above that. Like this. So we have one function that takes an a and a b and an x. Yeah, returns an int. It just returns x plus a plus b. And then there's another function that returns a closure called make incrementer, takes an int and it creates a b and then creates closure. how do you struct literals in C? C. This. Just call it. Oh, but dots inside. Interesting. Like, let's see. Probably we'll have to do it like this. Okay. Maybe not. But that's I'm just not going to question that. Like, this is just C being C, you know. Yeah, let's maybe try that out. All right, standard I/O. Sure, we can implement that, include that. Yeah, this should just be that. Okay, yeah, seems to work. Cool. Then, yeah, so let's say we have some condition. So if, I don't know, argc is larger than 2, then we call make incrementer. Alright, we don't have if as expression. Otherwise, constant 5, maybe. I'll make a constant function. And this is supposed to create a function that also takes an int and returns an int, so it has the same signature, but it just always returns 4. So how would that function look? Closure make constant fun. Yeah, it takes in a constant, let's call it C, and it creates a closure. But hang on, this captures different variables. So the way that we need to do that is basically we have one variable for the captured variables, and this is a void pointer. So just, you know, a pointer where we don't know the type, like this. And then I don't know, int to int closure accepts a function that just accepts these capture variables and the additional int, and it returns an int. So really, we need to like allocate memory for the captured variables. Which means for each closure there will be the actual code and there will be a struct. This, I don't know, contains the A and B, and then this up here just receives a pointer to the captured variables. And then it, you know, it gets the captured. It kind of casts that to a struct to these. Hang on, let me make sure I get this correct. So we cast the void pointer to a pointer to incrementer captured, and then we dereference that. And what we get back is, well, of course this has to be declared above that. And type deft. Let me just do it like this. Yeah. And when making an incrementer, we actually have to allocate memory for this captured thing. Yeah, I'm not going to do a lot of error handling right now, but basically we save, like copy these local variables to the captured part, and then we can associate these captured variables, this struct, with the function pointer. Oh yeah, it's a pointer. So it has to be like this. Yeah. Let's just make sure. This does not work. Yeah, standard lib for malloc or something. Sure. Yeah, end-to-end closure has no member A. That is true. Huh. Right, here it's just a.captured. Right, and we'll basically have to do the exact same for a constant function. Except this will not be incrementer captured, but let's call it constant captured. It's only a single C, and yeah, this will be constant code, creates constant captured, and it just returns the C and ignores the input. And make constant fun, then sets those and returns them. Yeah. So we can do this. And if we have more arguments, we should, yeah, fall back to the other function. This is basically what closures are. When someone tells you, well, I have a function or like a closure that takes an int and returns another int, what that closure really means is it's just a struct. It's a struct that contains an actual function pointer, like a pointer into the machine code that can do some things. But because that machine code can rely on local variables, it also may need these local variables, and those need to be passed around with this function. They basically belong to that function, they belong to that closure. So yeah, a closure is just a bundling of captured variables and a function pointer. And then, you know, we can create closures by getting all the captured variables, like creating this, creating a closure-specific set of captured variables. For example, for the incrementer, the captured variables will be different ones than for the constant captured. And yeah, we just create that, like actually allocate memory for that, copy all of the like local variables that we need into that struct, and then put that into this closure thing. An important thing, this captured right here is a pointer to incrementer captured. Whereas this captured, it's really just a void pointer. So it's less specific. The type is not specific anymore. We do type erasure. Here we know we have a pointer to this captured thing. But then in here we just say, okay, it's any pointer, it's just a void pointer. And then back in the actual implementation code, we take that void pointer and we can downcast that to the specific type that we had down here. And we know that's correct because when we create a closure, we always associate the correct code with the corresponding struct of captured variables. So here for the incrementer function, that's the incrementer code and the incrementer captured struct. And for the constant function down here, that's the constant code and the constant captured struct. And that's basically, when you create a closure in Rust, this is what happens under the hood. The compiler will create a struct of all the captured variables of that closure. It will create a function that takes this captured thing as the first argument. And then the actual closure code will just, before creating the closure, it will create this captured thing, copy all of the local variables over, and then create closure by just associating that with the function pointer. Right. Yeah, and each call to a closure, the compiler knows that you don't call some top-level function, but that you call a closure, and then it will actually parse this, get the function pointer of that, and pass in the captured variables as an extra argument at the front. Yeah, that's pretty cool, right? Yeah, we'll do that in Plum very much the same way. So I guess the first thing there would be deciding on a syntax, and the usual stuff, going through the entire compilation pipeline, parsing that syntax, then type checking that later on, and generating code, and so on. Yeah. By the way, I think that's pretty cool that you can have this, this expressiveness of closures, and in the end it can just be compiled to top-level functions that pass around values. That's nice. Right, so let's do that. Yeah, our compiler stages are the bacon and breakfast things. Yeah, let's actually think about how closures may look. Yeah, because Plum is an indentation-based language, I kind of want, I don't want braces around them, In Plum, everything is indentation-based. Types, indentation-based. You don't need, if you have an OR type, or like an enum, with 5 variants, you don't need to write 5 of these types. Just write 1 at the beginning and then indented all of the variants. Or when switching on a value. Or when creating a struct. Yeah, so I want a closure to be similar to that. Basically have some leading thing that tells you, hey, this is a closure, by the way. And then the rest is just automatically part of the closure, as long as it's indented. Yeah, I think the way, think Rock has a pretty nice syntax. Like in general, the syntax is kind of inspired by Rock. Yeah, let's maybe go to the, I guess, tutorial. Closure. Can we just look for closure? Nope. Function. No. I think they use a backslash. Yeah, I can just search for backslash. Yes. So this is the function and closure syntax in Rock. Have a backslash and then the arguments. To be honest, I think this looks kind of weird. So also that there's a comma there. But then when you use that, you don't have a comma. Interesting choice. Yeah, I think like we have a pretty nice syntax for functions. I think it's kind of, it takes some getting used to, but once you have it, it's nice. Yeah, and I think I like that it mirrors the call sides. Like when you call a function, it looks similar to how you define functions. And I think this will also get better with syntax highlighting when the function name has a different color than the arguments, and those have a different color than type variables and so on. But that's another story. Okay, so I think let's go with backslash. I kind of like that because it represents the lambda symbol somewhat, like the lambda calculus. Yeah, lambda calculus, you can define a function using this lambda. And the backslash kind of looks like that. So I think that's probably also why Rock chose that. Right. So maybe use that to create a closure, and then put all of the arguments in here. Like, yeah, let's maybe port that, like make incrementer takes an A or just an int, and it returns. Oh, we'll need to figure that syntax out as well. Yeah, and it just, this would mean it creates a closure that takes an A and returns an int maybe, and that equals something, and then here's the indented code for that closure. I think that would be nice. Oh yeah, it takes, I don't know, B, and it returns A plus B. Yeah, let's put them on the same thing. Something like this, perhaps. No. Yeah, make incrementer of 2, and then call let's call that inc, and then call inc5, I guess. That's the result, and then result to string is what we return. Yeah. I think that's pretty cool. Yeah, contrary to functions that can be recursive and so on, closures cannot be recursive. So you wouldn't we could also say for closures, you don't write the return value in there. And we just figure that out based on the body. That probably makes life a little easier. Yeah. But I do like using the equals sign to separate the bodies, just so it's consistent with the rest. Like we could do something like this, but then that's like here it's a type, and here it's like the actual value. That's let's do it like this. Okay. Oh yeah, for the type, maybe just literally do this. Like I don't know, return function that takes an int, returns an int. Like this seems pretty obvious, and it's also consistent with using this to denote the return type of a function. Okay. Yeah, I think I like that. Nice. Okay. Cool. So let's just see where this fails, and then work from there. Right. So we want to run the compiler. Compiling the compiler, and then running the compiler. Okay. Oh yeah, so this doesn't work. True. Yeah, so when parsing types, we need to parse function types. Oh, and here's naming is difficult, So we have names like function, closure, lambda. What do we use for what? I think it makes sense. Like these top level things, they are functions, definitely. We could say closures are also functions, really. Just naming wise. Yeah. Technically, closure is not the correct term for that. Because let's go back to the C code. Technically, a function closes over local variables. Closes as in the function code depends on that. And in mathematics, there's this concept of a transitive closure. And that basically means that if a function depends on some value, and that value depends on some other value, and it may even depend on some other value, like basically looking at all of the dependencies, like deeply into the dependencies of a function, that is referred to as a transitive closure in mathematics. In a graph where you have some set of nodes, then all of the referenced nodes, if you follow their references as well and their references, whenever you're done with that, you get the transitive closure of the original nodes. And closures kind of work in a very similar way. When we capture these local variables, really we are looking at the transitive closure of all of the variables that we need from the local scope, and we need to copy that into the captured part right here. In our case, that's not really true. It's enough if we capture the immediate values, because in our case, these variables can't be mutated. So that means that if we have some variable, I don't know, C, that is some complex thing but then it also references B, like it contains an actual like C reference to the B up here. We would need to copy that B into the captured thing, even if the closure only references C, because the B also needs to be kept alive. In our case, though, because we use reference counting, I think I removed that when I moved to the bytecode interpreter. Yeah. Anyways, in our case, the C would basically hold ownership or have a reference, increase the reference counter of B. So we can just copy that in here. We don't have references to other local variables, which can then be mutated or something. But yeah, that's basically where the term closure comes from. It's the transitive closure of all captured variables. And that means that technically, this part right here is the closure, only the captured thing. And this right here is basically, it contains the closure, like the transitive closure of all variables that are needed for the function, and it contains the actual function pointer. So closure is perhaps not I think it's the most widely used term, but from from looking at the origin of the term itself, it's not really accurate. So I tend towards going with either function or lambda. Function is usually not chosen because you already have these top-level functions. And just from a mathematical perspective again, these closures tend to not work like functions, which means that if you give them the same input, they don't usually produce the same output. Global functions don't as well. Like if there's like global mutable state, they can also return different values. But for closures, that's more obvious, that they can have some internal state and mutate that. So function is usually not a term used for that. In our case, though, closures are deterministic. If we create a closure, then if we call that closure with 5, we know for a fact that if we call that with 5 again later, this will produce exactly the same value. So this is actually this is a function in the mathematical sense. Right, so closure, probably not. Like my mood of this is nope, not like that. Function, yeah, it is a function. Although, of course, these top-level things are also functions. And maybe it makes sense to have some sort of distinction in the name. So lambda would also be fine. Yeah. And lambda is also a commonly understood term for that. Like I think in Python, there's even a lambda keyword for creating these closures, lambdas, whatever. Yeah, you use the lambda keyword for that. So I think I'm actually gonna go with lambda. Yeah. Oh, also makes sense because we use the backslash, and it looks like the lambda abstraction right here. Okay. Yeah, closure commonly used, but technically not accurate. Correct. But clashes with top-level functions. And this is correct. Yeah, so let's go with lambda, I think. Okay. Plum. We have the bacon, which is really just the lines of the file with annotation. Based on the annotation, it's passed into a tree. Next, we have the toast, and in here we probably have some parse type atom and parse type expression. A type atom is something that doesn't contain white space. An expression can contain white space. So for example, if we have something that is a list of t, this is a type expression, not a type atom. And yeah, for parameters, we only allow type atoms, which means if you want a space in here, you need to put parentheses around that. Because parentheses basically mean that an atom can have parentheses, and then inside of that have a whole type expression, which may contain white space again. Right. So I think for closures we want something very similar. This is a type expression, which means that basically you need to put spaces around that if you want to use that in here, for example. Which makes sense because here the arrow already means return type of the function. Okay, so higher order functions would look like this, for example. Makes sense. Okay, so this is not a type atom, but a type expression. And what does it do here? We pass a symbol, if that is some name. Then we have the arguments, which again we pass some type atoms here, okay. And then we pass a call. Yeah, that's fine. Like that's list of int, for example. First list, then the arguments can be normal, like any types without white space. And then we have passed the type call, like a call on the type level. I'm just wondering why, if I just write int in there, is that a call with no arguments? Because parse symbol would work. And then I think so. Interesting. Interesting. Okay, I guess. Yeah, and otherwise we just parse a single atom. Yeah. Yeah, and basically I think, yeah, and here we want to then also try to parse a function. If parser dot was it consume this is sum, then we are gonna return, hey, we just passed a toast type lambda. That's what we're gonna call it. Probably contains arguments and return type. Yeah, so we need to do this again as atom, or no, this is a bad input. Expected the return type. The lambda return type. I don't know. And then we have the lambda and so on. Okay, and this is the return type. Okay. Yeah, does this make sense? Let's just think about this. For example, I'm not sure about how, what about this? this is I think this will be passed as int of int, you know, like list of int, you know. So if there's I'm not sure how to do that elegantly. That kind of sucks. What? How? I mean, we could say we have an introducer thing. Yeah, this is a lambda that takes an int and produces an int. Would work. Maybe I'll change that later on. But I like that this is kind of obvious. Yeah. And we can basically check, is this, like, if we find that, then we only pass atoms. So a list of int would be passed into two types, like list and int. And you need to put parentheses around that if you want those to behave as a single argument. Yeah, that makes sense. That makes sense. Okay, so yeah, let's maybe not do this exactly, but if parser dot consume backslash, then we do some stuff. What stuff? Well, we parse arguments. List of toast types, correct, and then atoms, yeah, they can't contain white space. We push, like we parse them until there is nothing afterwards. Then we expect there to be this. Yeah, that's maybe don't need that. Okay. Yeah. Not sure what's going on here. After string interpolation. Oh no. Yeah, makes sense. Makes sense. Or bad input. Wrong. Expected. Number. Arrow. Boom. Yeah. Okay, and then there's the return type. Makes sense. And then we passed a lambda with the arguments and the return type. Okay, that seems reasonable to me. Let's check if this works. And it doesn't, because oh yeah, there is no type, toast type lambda. So our toast types, they can be variable, which is just a string, a call, a struct, an enum, or a lambda. Toast type lambda, and this toast type lambda contains the args, which is a slice of toast types, and a return value, which is a toast type. Beautiful. Toast type lambda refers to T. It does. Oh yeah, basically, I think while I was typing. Oh, let's see. Yeah, let's maybe turn that into a reference so we don't have an infinite loop, and the language so it doesn't like loop indefinitely. Okay. Oh man. Yeah, I should fix that, but okay. Yeah, toast type lambda. Next. Yeah, this is a toast type lambda, return value. Oh no, return type. Return type. Nice. Oh yeah, and return type is return type put on heap. Beautiful. Cool. Now these should be parsed, and we also want to print them. So write toast type. Yeah, if this is lambda, then we do something. We print a backslash, and then for each argument in the lambda args, we basically print a space and then the argument. Yeah. And then we print this arrow and then the return value. Return type. Cool. Oops. Yeah, so in the next compiler stage we don't handle that. Completely true. Yeah, when converting a toast type to a plum type. Yeah, we switch on the type, and for lambda, compile lambda type. Just put a to do in there, and then I first want to work on the parsing. Yeah. Okay, so the type is parsed. Next up, the actual expression. So how do we do that? I think for now let's enforce that all parameters are on the same line. We can probably relax that later on, but yeah. Maybe that the body is on a new line. Yeah, seems fine, I think. Okay, so this will be I know there is the parse expression. Yeah. Oh yeah. Parse unpiped expression is what we do first, and then we parse all of the pipes. Is that correct? Yes. We could, for example, do something like this. No. I don't know. Could have a function 1 with 5 that takes a closure and, sorry, a lambda, and calls that lambda with 5. And that should work. Close this, yeah. Okay, so we want to parse a lambda and then parse pipes after that and so on. Yeah. Okay, so yeah, parse unpiped expression. Here we want to add that lambda. Expression is parser.parse atom. A lambda is definitely not an atom because it contains spaces. And then there are arguments, which are other atoms. Okay, and an atom is, you know, parenthesized thing or int or string or name or symbol. Okay, I think basically what we want to do is yeah, that doesn't have to work. Parser.parse lambda. Like if, you know, if parse lambda is some lambda, then I don't know, return something like this. And the question is, what is this parse lambda? Okay, and let's get this. Yeah, one thing I'm wondering is, parse these atoms. Unpiped expression, is that what is allowed to be inside of the... Oh no, here we call parse expression inside the parentheses, because this may contain pipes. Okay, yeah, I was just wondering where parse unpiped expression is used, but it's really only used down here. That's fine. Alright, so parse lambda. Yeah, that probably it's gonna look similar to this. Yeah, expressions and then the types. So parse lambda. Takes a parser, returns a maybe toast expression. Okay, so let's maybe add that to the toast expression kind. Whoa, you have int, string, struct, member, symbol, and switch. Name. And then maybe here, lambda is toast lambda. Yeah. Because it's kind of, you know, these first you define something like a struct, and then you get the member of that. First you define something like a symbol, which get converted into enums, and then you switch on that. First you create a lambda, then you call that. Seems reasonable. Okay, so above call, and here you have struct toast lambda. A lambda, I think, has parameters very similar to, like, they have a name and a type. They're exactly like these. Crazy. Yeah, it doesn't have a name and no return type, but I do think a body, which is a toast expression, probably a body. Yeah, that seems about right. Wow. So body toast expression. Nice. Toast lambda, yeah. Refers to... Oh, again. Again. Oh, man. Yeah, I need to fix that sometime. Toast lambda, fine. Yeah. And then parse lambda really returns toast lambda. Beautiful. And what it does is basically it tries to consume a backslash. Or if that doesn't work, it just returns no match. like this parser doesn't match, there is no lambda there. Otherwise, we know for sure it's a lambda. So then we pass the parameters, which, I mean, how is a function passed? Wait, how is a function passed? Oh, it's like in the yeah, like this. You know what, let's factor that out into parse parameter, this part right here. Passing a name, then a colon, then the type. Yeah, parse parameter. Parse param, yeah. Returns toast param, and it's just this. Takes a parser, then it just does parser.parse name, or return no match. There is no parameter here. Otherwise, we just consume the colon, yes, perfect, and then the type, also perfect. And then instead of pushing that to some list, we just return passed. Crazy. Yeah. Cool. And then up in here we can say parser.parseParam a break. And we can even push that directly. Look at that. Beautiful. Oh yeah, this can fail. True. Yeah. Nice. And we probably want something very similar for our lambda. So we pass the parameters. Yeah. And then we expect an equal sign. Or otherwise, we say, well, this is a bad input, bad toast lambda. Yeah. And then we actually do something. Oh, hang on. Yeah, the question is kind of, if this is a multi-line lambda, then this will not be, contained to a single line, and no, instead we need to pass this on the bacon, basically. Like not on the a parser only ever spans a single line because we have this tree of lines. And hang on, in here, yeah, normally these things take a bacon. Yeah, I should refactor some of this as well, but yeah. Yeah, so I think what we actually want is some sort of parse lambda that looks similar to this. Pass a lambda with a bacon, basically meaning a subtree of the file based on the indentation. And in here we turn this bacon to an expression. And this is, for example, where we parse a struct by looking if there's an AND here, and then doing things based on that. I think we need something very similar to, like, if bacon to lambda is some lambda, then return parsed lambda. Yeah, okay. And then here parse lambda would really just create a parser basically for this line. How do we do that here? Like this. And then consume the backslash and the parameters and the equal sign. And then there are two cases. Similar to how struct works, I think. Yeah, similar to this part. Yeah, this is a mutable parser. And then the body, basically we check, does this node have children? If not, then we want to pass an expression after that, the function body. Expected body of the lambda. Yeah, otherwise we need to make sure that there is nothing else on the line. So if we have, something like like this multi-line thing, then we pass this, we pass the parameters, the equal sign, and then we need to make sure that there's nothing coming afterwards if we also have children in here. Okay, so if we don't have children, then we pass the rest of the line as a single expression. That's what this part does. And then we should have consumed the entire line. Otherwise, if there are children, then there should be nothing, this should be invalid. Instead, if we have children, there should be nothing after the equal sign, and then we pass the children as bodies. Yeah, so there should be nothing after the equal sign, and then the children will just be the children passed to expressions. Yeah, this is not true, because a function can have multiple values and it just evaluates to the last one. And there is like a two function def or something that should have very similar logic. Yeah, this right here. Expected fun body. As we have this. Yeah. Oh, yeah. We'll just take this basically. Yeah. Okay, so yeah. And there should be nothing else on the line. We pass the children. If they are empty, then we are like, hey, this is bad equals source. We need that. Okay, so consume returns basically an indication of where in the source code that came from. And here we show an error at the equals sign, expected lambda body. Yeah. And this will be a toast expression. And then the body source is that, sure. And then this is a single toast expression, this body. And then at the end we can return a parsed toast expression dot lambda. Oh, not an inner type, hang on. How does that work? Oh yeah, toast expression kind at and then the source. So toast expression kind dot lambda something at the source, which will just be the initial, oh yeah, backslash source, which will be the entire thing from backslash source to body dot source. Beautiful. Yeah, this lambda will be a toast lambda, which means it has some things. It has a params. Beautiful. It has a body. And params are probably, that needs to be a slice. Yeah. Like this. Beautiful. Yeah, parse lambda, parse unpiped. Oh yeah, we should add that as well. You know, but for now let's just parse like multi-line lambdas using indentation and so on. Okay, to lambda does not work. There were no definitions. Oh yeah, because it's, yeah, some of these are called twos, some have toast in the name, even though we don't really need that. Some have parse, it's kind of a mess. I should refactor this file at some point. Okay, you don't handle, oh yeah, okay, that's a toast, I guess. Yeah, and here let's just handle that by just crashing. Compile lambdas is what we have to do. Beautiful. Okay, I guess we are parsing lambdas now. That's cool. Yeah, let's actually like print that maybe. Hang on. We have the plum, the toast, and then we print that toast. Oh no. Oh yeah, we can't print. True. Okay, let's see. Toast. Line 68. That has nothing to do with what we did before. Interesting. I don't handle type.struct. I haven't updated this in a long time, apparently. Yeah, struct is just an end of the fields. Name and type. Oh yeah. Sure. Okay. Yeah. We'll get there. We'll get there. Oh. That's cool. It's more readable, actually. Okay. String and source, yeah, no. I don't, apparently. True. I think I'll put the name down here. Yeah, symbol switch and struct. I guess for field in struct.fields, do something. Does it have fields or is it just a map or something? Yeah. Yeah, it's just a slice of fields. Yeah, here we print the field name colon and then the field value with more indentation. Indentation +2. Yeah, kind of like this. Yeah, like this. And also in front of that, like, is first is true if the first will have that in front of that, the others will just have more indentation. Also, if fields is empty, then it's just gonna print an and that's it. Oh, it is already a string. Yeah, I should also refactor the toast so that it's more consistent about where do we just have strings, where do we have strings and sources and so on. Okay, welcome to the Plum compiler to do. In the string thing. All right. Yeah, this is already not, like, this is not up to date. Yeah. For now, that will do. Yeah, there's the off thing of a member with indentation +1, and then, oh yeah, that's just member and the name. And the string of the name. Call doesn't work. Oh yeah, this should be dereferenced, I think. Okay. Seems to compile at least. Whoa. Okay, so that's, we call make incrementer. Yeah. Oh. Yeah, this is a lambda type, and it's a lambda. Yeah, for the lambda type, that's more maybe also print surrounding, you know, surrounding parentheses, like this. Cool. And then for the actual lambda, we should print useful things, like a backslash. And then space separated parameters, and then an arrow, no, an equal sign, and then the lambda, an equal sign, a new line, and then the lambda body, more indented. Kind of like this. This call doesn't work. Right. Right. So, main calls make incrementer. Correct. Make incrementer returns a lambda, and it creates a lambda where b is an int, and it calls a plus b and foo, which doesn't make sense right now, but you know. Okay, parsing works. Ooh. We can parse lambdas and also lambda types. Cool. Yeah, I'm gonna take a break, and then we'll continue to the next stage. Comment this out. Yeah, we'll continue to the egg. Nice. All right, I'm back. And I guess let's just continue with the next compiler stage. So we passed the toast and now the egg. Right. In fact, yeah, exactly. We have to-dos in here. And we basically need to think about how we represent lambdas in the egg. On the type level, the egg has plum types, which are common among the egg and the next compiler stage, the yogurt. So I think let's add lambdas there first. Okay, so we have primitive types, never struct enum, recursive types, and now also lambdas. Lambda, yeah. And a lambda type, yeah, that actually like contains, I don't know, lambda type, why not? And yeah, struct lambda type has args, which is a slice of plum types. And then it has a return type, which is another plum type. This time not crashing the language tooling by forgetting the ampersand and creating an infinite type. Okay, so we have these. Yeah, exactly. Now all of these functions, these type algorithms, they don't work anymore. So let's fix them. First, naive comparison of types basically stays the same, except that lambda types now also need to be comparable, I guess. So if we have some lambda type and another lambda type, well, they are considered equal if the arguments are the same and the return type is the same. So that makes sense. Then hashing types. Again, this is definitely not a perfect hash, but we'll just do something there. Writing types, lambda will be pretty similar to how it's done in the toast actually. Yeah, so when writing a toast type, we do this, and I think we'll do something similar here. So first the backslash, and yeah, then the arguments, and then the return type after an arrow. That seems fine. Okay, what's going on here? Plum types. Oh, right. Yeah, I guess let's do that. Dereferencing manually. Perfect. Now down here we have a concrete type and a generic type, and we want to see if two types match. So if the this is called if we look for a function, you know, using overloading and stuff like that. So more concretely, we have, let's say we have a lambda here, which goes from int to some type variable t, and a generic type with int to string. Then we want to match them and see that, oh, hang on, it's the other way around. Concrete would be int to string, and generic would be int to t, and then we figure out the constraint that t needs to be string. Okay, so some generic lambda only matches if the concrete type is also a lambda. Like if we call a function with an int or never, hang on, this can never be reached, right? Yeah. If our concrete type is never, then we immediately match. But if it's something else, then, you know, if it's a primitive type, then that doesn't match. We can't assign int to a lambda or a struct or an enum. We can only assign lambdas to lambdas. This is actually not to do, but it's unreachable by design. Okay. Because before calling this, the types are extended at the bottom, so we never reach the recursive types, like the recursive markers in those types. Okay, so we have lambda, generic lambda, and yeah, the concrete type needs to also be a lambda. And well, I guess then all of the arguments and the return type need to be compatible. That's basically it. So for args, I guess, in zipping the concrete lambda args with the generic lambda args, we now need to check that these match. Oh, hang on. Oh, it already exists for slices. And that is perfect. Yeah, okay, then we can just say concrete lambda args match against generic lambda args. Yeah. Nice, using the constraint and what we are currently matching to protect from recursive calls. If that doesn't work, then we just return false. Yeah. Okay, and if all of the arguments match, then we also need to match the return values. So this would just be the return type. I always say value, I mean the type, of course. Okay, and if that doesn't match, we return false, and that's it. Perfect. What is it? Oh, yeah, and I know why. I know why. Okay, cool. So matching types should work. Then specializing types with some substitutions. Yeah, for a lambda, we basically need to build up new arguments, which will just be a list of plum types, I guess. And then for each argument in the lambda arguments, we specialize that argument. Kind of like this. Push arg.specialize. Yes, perfect. And then in the end, we just return a plum type dot lambda with a lambda type where the arguments are the arguments. Of course, that's a list, so we need to convert that to a slice. And the return type is also specialized. Yeah, perfect. Yeah, this is not... Oh, yeah. We need to put that on the heap. Sure. But that should be the specialization. Next, extending types. True. Oh, and this is kind of more difficult, I guess. Yeah. Let's maybe copy the thing from structs and then figure out where things go wrong. So we have a lambda. Hang on. I'm just going to paste that here. So what we return is definitely a plum type lambda. Okay. The question is only what kind of lambda type do we return? It needs to have arguments and return types. And I guess the what do we do here? I don't know. Let's just rename this to argument first. Type that is the original struct, except the arg that we navigate into. Interesting. Interesting. So I guess you kind of have a list of argument types where we put things, where we push things inside, and then in the end the arguments are, well, new args converted to a slice, something like this. Yeah. And the return type is something else. Okay. You know what, let's just be super let's be naive and just say we extend those types at the bottom with this type. Does that work? I think it does. Yeah. So we have the new args. Yeah, something like this. And the same thing here, basically. That's just the lambda return type, and this is just the arg. And hang on, we can even do that inline. Yeah, let's do that here. Perfect. And we can remove this. Yeah, okay. So basically, if there's a recursive type, we don't just extend it one level, but we just paste our complete type down there, and that's equivalent. So that should be fine. Even though it's not completely like minimal, you know. But yeah. I think like we need some way to minimize types, a more general way to do that anyways. So I think maybe over time we'll even like simplify this function followed by a minimization or something like that. Yeah. Okay, so extending recursive types. Right. Here we have our lambda type with arguments. Let's just call them args. Yeah. That's just a list of plum types, and then for arg and lambda args we say this. Yeah, that's the push arg.extend recursive type level +1 and the extension. Yes, and yeah, then we'll just return the plum type dot lambda of our lambda type, where the args converted to a slice, and the return type is the lambda return type extended recursively. And put on the heap. Okay. Makes sense. Then replacing recursive types from some indentation level to some indentation level. I mean, that's just like, this is like stupid translation, just nothing. Yeah, let's simplify this into, like, make this more local. Yeah. And let's do something very similar down here. I will just say this is a lambda where the arguments have been replaced. So replace recursive level of this type. Yeah, from and to. Perfect. Now what's going on down up here? Cannot assign plum type to this. Okay. Sure. Then let's do it like this, maybe. That is equivalent logic, like the actual logic, not the caching and so on. So when are two lambda types equivalent? We have an A lambda, and then we have a B lambda, which is the second type. Okay, so far so good. Then we want to check that the arguments are the same. So that's basically this. Except this part. Let's maybe inline that because it's not really worth its own name. Okay, yeah, no, okay, so, yeah, then basically just check the return type. Like, is equivalent A lambda dot return type and B lambda dot return type. Beautiful. Yeah. Cool. Oh. The age-old dereferencing. Cool. Oh, hang on. Oh, yeah, because this is the last statement or the last expression. We can just evaluate to that. Whew, cool. And finally joining types. Ooh. I have not thought about that. But oh shit. How do you join lambdas? Like, assume we have one lambda that only accepts an enum with that is either foo or bar, and another lambda that accepts an enum that is bar or bass. we probably want to be able to join those lambdas into... No, hang on. Yeah, we should sketch something out for that. Okay, so let's say I have, I don't know, some lambda that takes an A, which is either foo or bar, and I don't know, produces an int. Yeah, I mean this is not valid syntax right now, but that's fine. And then I have this other lambda that either accepts, I don't know, bar or baz. Oh. Something like this, perhaps. And now let's say I switch on some condition, which is a bool. In one case I do something, in the other case I do something else. In the one thing I evaluate to this lambda, in the other case I evaluate to that lambda. What's the type of this expression? What's the type of foo? We could say foo is, I mean it's a lambda type, obviously. A lambda that takes an enum and produces an int. But we can't say this you can't pass foo into this, because if this is the second lambda, then we don't know how to handle foo. So this is not allowed. I think we want a lambda that only handles the common enum variance. Damn. What? Okay, and if one lambda returns, I don't know, it always returns. Oh, yeah, by the way, let's choose more crazy parts in here. This is B or C or D. I think that's easier to read. Like the common variants are B and C. These are the values that both lambdas can handle. So this is what this lambda accepts. And let's say it produces either X or Y, and this produces either Y or Z. Then the resulting lambda can produce X or Y or Z. Right? So these are joined, like we currently do when joining types. And these are like joined in a different way. We take the intersection of those types. Hang on, there is, like, I think this is the typical, what's it called? Contravariance, covariance, and invariance. Yeah. Yeah, this is kind of subtyping, right? Not like in an object-oriented sense, in we copy state and behavior and so on, but more like we have a type being a set of values, and one set of values is a superset of another set of values, or a subset of another type. We have that. That's basically our is assignable to function, which is also somewhere here. Yeah, is assignable to. Yeah, because types are just sets of values. They don't have identity. We only have structural types. And if all values of one type are also values of the second type, meaning the first type is a subset basically of the second type, then that's considered assignable to the other type. Yeah. Okay. So so here, list of cat is a subtype of list of animal, because the list type construct is covariant. The subtyping relation of the simple types is preserved for the complex types. That's basically what we have what we have for the return values of functions. If, let's say, like this is a subset of this function, and like let's assume they accept the same argument, then the set of these functions, like this type, is also a subtype of this type, meaning that because every value of this type, like an enum that is x or y, can be assigned to an enum that is x or y or z. That's the reason that each function that takes some arguments and then produces an enum x or y is also a subtype, or can be assigned to this type, to a function that produces an x or y or z. So the return types are covariant. As the relationship between these simpler types is the same relationship as for these complex types, covariance. Whereas the parameters, I think, are contravariant, like this. A function from animal to string is a subtype of function from cat to string. That's a subtype. Yeah. Subtype. Yeah, a smaller set, basically. Because every function that takes an animal and produces a string is also a function that... No, hang on. Hang on. That's a subtype of this. Oh, yeah. Every function that can take an animal and produce a string is also a function that can take a cat and produce a string. Because a cat is just a more specific version of the animal. So you can kind of treat this function as a function from cat to string, because it behaves exactly that. If you give it a cat, then this function produces a string. So yeah, this can be treated like a function from cat to string. So the parameters are contravariant. Yeah, and for now, I think we'll just go with invariant, meaning that that they have to be the same. Like the parameters just have to be the same. Makes life easier for us right now. And yeah, let's also say the return values are the same for now. We can change that later on, but yeah, in the long term, we want the parameters to be contravariant and the result, like return types, to be covariant. For now, let's just make everything invariant and then relax that restriction later on. Right, okay, so you don't handle plant type.lambda exactly. So case, let's say we have a lambda, then the other thing also needs to be a lambda. So yeah, B also needs to be a lambda, or we say this doesn't work. Okay, and then we check that the arguments are the same. So a lambda args equals, and this is like an exact comparison, you know, the naive comparison that we do up here. They have to be exactly the same type. If for now, if you have a switch and one branch evaluates to a function from true to something and another like I don't know, string to true, and the other is a function from string to false, those are not compatible right now. Later on, we'll make them compatible. For now, the arguments have to be exactly the same, and the return type has to be exactly the same. Okay, yeah. And then we can just return the original type. So, what's it called? Type was called A. Yeah, because A, oh wait, yeah, we can just check A. Well, both have to be I don't know, something. What we'll add a to-do in here, make parameters contravariant, return type covariant. Beautiful. Okay. Yeah. Equals to plumb type true. Should be like this. Yeah, that should probably work. But that's only the types. The next step in the egg was to actually compile lambdas, and there was some to-dos in here. Yeah, so compile lambda type and compile lambdas. I think the lambda type is quite straightforward. So I guess let's just do something very similar to that up there. Meaning we have the arguments, which is a list of plum types. And for each argument in the lambda arguments, we basically push that into the list after converting it to egg. Okay. Yes. And then we have the plum type lambda with a lambda type with our kind of mapped arguments and the return type, which is lambda return type. Dot to egg like this, and also that return type. No, one too many. Okay. That's the first to do. The second to do is compiling lambdas. And okay, so the question is how do we do that? I mean, the egg has a list of top-level functions. I think this is already, this is already the place where we want to compile an egg closure, a lambda into this closure of captured variables and a top-level function. Yeah. So this will actually be just a function. We will compile the closure body as a new function. that takes some egg params. Yeah. Okay. I guess let's just let's just start with the function body, and then we'll go from there. So what do we need to do? We need to basically build, make a struct containing the captured variables, aka closure. Compile the lambda body as a standalone function that is like top level, and that takes the closure as an explicit argument, and then create a lambda based on that. That contains both the function, the compiled, the closure, and the compiled function body. Yeah, kind of like that. Okay. Yeah. I guess let's just create a struct. And that should be similar to what we do up here, maybe. So the one thing I'm hesitant about is that this is not as type safe, So in our C code, we create these captured things, and here we assign that typed pointer, pointer to constant captured, or in this case, pointer to incrementer captured. So there's a very specific closure, and we assign that to a void pointer. So we remove type information. And then later on, inside of the function that accepts this void pointer, we then cast that. We need to do that in a safe way in Plum, because we don't want to allow like arbitrary casts between different types and so on. Because right now we trust that the egg is always created correctly, and the yogurt and all of the stages. But at some point I want to have this built-in compile function, something like this, where you can pass in some sort of bytecode, and that gets compiled into an actual function. Which means that at some point in this compiler pipeline, at some point in here, we can probably also, for example, generate the yogurt based on this high-level bytecode. Which means we can't trust the data in the compiler stages to be generated from source code, and it should still be type safe. So maybe we need a concept of a closure or something. Yeah. Like having an explicit concept of closures in the egg still. Yeah. Yeah, okay. So maybe here we have some I don't know. Let's sort them that way. Some sort of, let's call it closure instruction, you know, that has both, similar to the struct, like a list of egg IDs that are captured, and then also the, like a pointer to a function or something like that, or a pointer to, yeah, pointer to an, like, or like the name of an egg fun, basically. And the compiler can check that this closure instruction is valid. You know, that the amount of egg IDs that are captured in here, that you put in here when creating the closure, that those match the number of parents or something like I think we have a separate call closure instruction as well, in order for that to be type safe. Maybe. Okay, well, let's maybe first back off and check what's going on here. So egg expression kind refers to egg closure, but that type doesn't exist. True. So we want to do that. We want to have an egg closure, and that should, and I think lambda is the correct term here too. And the lambda contains the closure, let's call it captured. And that's like similar to the arguments of a call or a tag. These are the captured variables. And then we have the function. Which is a string. Yeah, okay. It does kind of worry me that we don't have any sort of type checks or something in here. not sure how, like what exactly to do here. I think this is fine. Captured. Yeah, okay. So we basically omit this closure instruction. That's the idea, right? Or like lambda instruction. Egg lambda, where captured is something and the function is also something. Yeah, I think, yeah, so let's think about how to compile this function even. Sure. Egg lambda. Well, no, that doesn't make any sense. This is a function. And what function? Well, we kind of define that here. Yeah, we want to compile the closure body, but first we want to analyze like what variables are used from the outer scope. Let's see, how does that even work? Like, yeah, we don't have any like global, like all names have been resolved here, except which functions to call, because that depends on types. I guess. Okay. So I'm kind of struggling with this, to be honest. But I can do this. I can do this. Okay. Let's see. Okay, we want to analyze the lambda for which names outside of that are referenced. And that's basically related to variable scoping. So we have this list of visible variables, yeah. And okay, here we convert some toast to an egg, sure. Toast type to an egg, also sure. And then built-in functions, sure. And then the egg body to an egg, and egg expressions to an egg. Maybe something like first I think we want to go over the body and just collect all of the captured variables. Like which variables from the outer scope does this function capture? And then we can just go from there. Okay, so egg code compiler. Yeah, I think we want something even more basic, like push param to egg. Okay, sure. Oh, that's it. Okay. So let's add a new function called, yeah, that's similar to this. That just says collect captured or something. And it takes a toast expression oh, right, the body is also an expression. That makes sense. I was looking like where is the compile body or something, but of course the body is, yeah, here the body is just an expression. Okay, so collect captured, yeah, I guess. And that should just be a collection of strings. So let's maybe pass in, you know, a mutable list of string. These are the variables that are captured by this expression. Yeah, we don't need this because we don't want to emit anything. We just need the visible the visible variables. Yeah, and then we basically want to do this, but we will strip that down a lot. So first of all, if it's an int, we don't care. If it's a string, we don't care. If it's a struct, now it gets interesting. Now we don't want to map the fields or something, you know. We're just gonna go over the fields and collect the captured things of them. So field.value collect captured, using these visible and captured parts. Yeah, something like this. And for member, very similar. Member.off.collect captured of visible and captured. Yeah, the name is just a string. Symbol, don't need to do anything. Switch condition, collect captured. And I'm just gonna replace all of these calls with collect captured. Perfect. Yeah, on the condition, on the cases. Yeah, which means we snapshot the visible. That is important. And then for each case body, yeah, we don't need a compiler. But yeah, we do this. We define those variables. And then we collect the captured ones of that compiler using those visible things. Case body, yeah, it doesn't matter. And then we restore them. Okay. And then, yeah, this also doesn't matter. Okay. Oh, I see. Yeah, let's maybe say collect. Have something like a getter, you know, captured variables on a post expression, and it returns a slice of string. going to call toast expression dot collect captured. Yeah, it's going to create a list of strings and then say collect captured of visible and captured, and then convert that to a slice. Yeah. Oh yeah, this doesn't return anything. True, these are pretty useless. Yeah, if so we start off with an empty visible thing, like no variables visible. And if inside of that lambda, you have some sort of body, lambda dot, yeah, if inside of that you define a new variable and then later on you use that, that's totally fine. We don't we don't want to return that here. But if you reference a name that doesn't exist, then we just push that to the capture. Like this. Huh. That's pretty neat. Okay. Yeah, for lambda, we should probably define all of the parameters, similar to how we do that in a switch, by the way. So maybe look here for inspiration. I guess. Yeah, we snapshot our visible variables, and then for each parameter in the lambda params, we define that parameter as something. Oh, yeah, the IDs don't even matter. Like visible could just be, I don't know, a hash set or something. Well, but something similar. It doesn't need a payload. Yeah, I guess I'm just gonna put egg ID, I don't know, enters -1, something. Again, horrible, should refactor that. To do refactor. Yeah, okay. Oh, right. So if we have nested lambdas, like let's say we have a lambda here, and this then creates another lambda that then uses A, for example. That means that the outer lambda also captures A. So it can then create the inner lambda. So the outer lambda captures something from the outer environment as well. That's the idea. Okay. Yeah. So we have the arguments. Yeah, we don't need to push them or anything. We just need to collect the captured variables. And then the receiver, if it's a name, then something. this is an error, I guess, will be handled not during collecting captures, but during compilation. Something like that. Okay, yeah, variables are defined. Same invalid egg ID here. Let's maybe just define that up here, because why not? Beautiful. And for the expressions, we just collect the captured variables of those. Okay. Okay. Some more green tea. We have parameters. Oh yeah, this just push an invalid egg ID, that's fine. Yes, and collect captured of, I guess, the visible and the captured things. Then restore them. Perfect. In here we have this case evaluates to nothing, but previous cases to egg ID. True, maybe. Yeah, this lookup, sure. Yeah, okay, I guess let's, if this is none, then yeah, I think that's like more readable anyways, so. Okay, yeah, parent.string is not a thing on, yeah, that's just the name, and this is that, and then we have, that's basically it, right? Oh, no, not name, not string. Well, I guess. True. That's the lambda body. Okay, so now we're back up here, like we are here. Captured is lambda.collect captured variables. Boom. And we have a list of strings. We basically get the corresponding egg IDs, similar to how we do that here. For, I don't even know, name and something like this. Oh yeah, this could be. Oh yeah, the same variable can be in there multiple times, of course. Oh yeah, for now I think that's fine. Also, we're just gonna print lambda contains like captures and those strings. Cool. Yeah, this is the lambda, not body, because Nope, because the body can reference the parameters. So it should be toast. Yeah. And then for each of those captured thing, unknown captured name that. Okay, and we're just gonna underline the entire lambda for now, which I guess later on attribute to concrete source. More precise source. Yeah. Okay, so basically we figure out which variables the lambda captures, aka the closure, and look those up in the current scope. Fantastic. And these are like the captured names. I think we should also have captured as a list of egg IDs. And then here we look them up, and then we say captured dot push that ID. Okay, so here we have a list of egg IDs which the function wants to capture, and by putting them down here in this expression basically means, hey, create a new kind of value, similar to how the struct expression creates a new struct, and the symbol expression creates a new symbol, and the int expression creates a new int, and so on. The lambda expression creates a new lambda by capturing these values here and associating this closure with a function pointer. Yeah, associating these variables with the function pointer. Okay, so lambda dot body, I guess. Oh yeah, the body needs to be compiled to a function. So up here we have this kind of thing, you know. I think we want something very similar. Yeah, something very, very similar. Yeah, so the lambda body as a standalone function that takes the captured, the closure captured variables as an explicit argument. So here we just create a function with the name, I don't know, closure something. Toast. Oh, yeah, we can just, that's crazy. Closure, add, and then the source. Let's do that, because we just need a unique name, you know. And this basically says, well, this is the closure from this part in the source code. That should be unique. The parameters are the actual lambda parameters. Let's call it lambda. Sure. And push those. Yeah, that seems fine to me. The only thing is the first parameter should be, you know, the captured thingy. Yeah, params dot push param dot I'm not sure, param dot something. I'm not happy with that, because then we lose. I'm not sure how to recover that type information, because I don't want to add, you know, basically like a downcast expression or something in here. I don't want to say, hey, this function accepts something like like a void pointer, as the first argument, and then we cast that void pointer to something. I want this to be like typed in a like safe, verifiable way in the compiler. Not like I don't want to have a generic downcasting expression, basically. Okay, what if every function has captured variables? Every single function, like every egg fun. And that's just a list of, I don't know, egg IDs or something, similar to parameters actually. It's just, you know, egg IDs with types. But like normal functions, they don't have any of them. It's just an empty list. And for those closures, we actually set them. Yeah, I think I like that more. Because then in the egg closure expression, egg lambda expression, we can check that these captured egg IDs have the correct types and correct length and so on for the referenced function. So we can look up the function, see what kind of captured variables it expects, and then yeah, that should just work. Like param has a string and a type. Yeah, here I think I just want a type and that's it. They don't have any names, any meaningful names at least. Okay. Okay. That's cool. every function has captured, can capture something. By default, functions don't, but closures do. Yeah. Then in here we can compile the parameters as usual, only the captured parameters, they are this list of IDs. And now we actually want their names, captured types. So these will just be basically going over the, hang on. We have the ID. I think we can do compiler or body dot. Oh yeah, we don't have types yet. True. Okay, I guess let's not do that this way and just say just ignore them. Right. That seems interesting. Or at least maybe have non-captured, maybe. I don't like this. I really don't like this. You know what? Let's maybe go through an example of what that might look like. So let's say we have a function list, like map. Yeah, it takes a list, which is a list of t, and it takes a mapper, which is a function from t, let's say list of a, from a to b. Yeah. And then this gives you a list of b. And there's something inside. Okay, basically, let's maybe also say we call that with make. Like, okay, we should be able to do list 1, 2, 3 map with a lambda that takes an number n. Oh yeah, let's maybe in here say increment is 2 and returns n plus, it's really just like this. Yeah, so now we have a list of 2, 3, 4. What would actually happen here? I think this would become like And this is not even like type checked or anything, you know. Yeah, it's really just, I guess, a function that takes like a top level, you know, lambda at something that takes an increment as a captured thing. So this is like a hidden parameter, basically, and an n. And then there's a body that takes 2 arguments. And it can basically say, well, you know, we call, I don't know, plus with 0 and 1, and that's basically it. And then this would basically translate to, you know, 0 is this, like the increment thing, and 1 is, you know, basically the list. And yeah, this will be more expressions, and like in reality we first create the 1, then the 2, and so on, but for now let's just say it's like that. Now we create a closure. Let's say lambda capturing the 0, something like this perhaps, and also the name, yeah, down here, lambda at something. And then when we call map, we can pass that original list and that. Yeah. And that seems reasonable. Yeah, it's just that what are the types? This is int, this is list of int, this is int to int, and this is list of int again. This is int to int. So the thing is, we don't know the types of any of these yet. Of any of these. I'm not happy with that. Not at all. I guess man. How do we do that? I mean, the other option. Yeah, the other option would be to keep the nesting here, not create this function down here, but just keep that inline in here for now. You know, like this is, I don't know, a lambda that takes something, that takes a 3, let's say, and it returns plus of 0 and 3. So this can reference IDs from the outer scope. And then only in the next stage, when we type check things and so on, and monomorphize functions and whatever, that's when we turn these lambdas into global functions. We could do that. Maybe that's the easier solution. Yeah, okay. So, yeah, not this. Yeah, let's undo this here. Yeah, like switching that around I think was correct. Yeah, and the lambda does not have this, but it has instead an egg body inside. Simple as that. And it has params, of course, which is a slice of egg IDs, very similar to functions. Oh, hang on. The body already has params. And expressions. Egg code. Oh, yeah. Yeah, okay. I think let's just say it's an egg body, and that's it. Lambda just takes an egg body. Fine. A body that's not executed, but is, you know, later on something happens with that. Which means we don't need to have this collection down here. We will add that to the next compiler stage, I think. So I'm just going to comment that out for now. Yeah, up here lambda types, yeah, that stays exactly the same. Okay, so if there's a lambda, I'm just going to copy that, comment that out as well. We don't need to do any of that. Instead, we just compile the body. Quite similar to the switch, by the way. So we take a snapshot of the invisible variables, and then we say the body is basically the lambda body. Hang on. What's going on here? Here that works because we take our body, which is, you know, the body builder. Oh yeah. Yeah, we want to do the same. Just body.parent.egg compiler. And then for each parameter in the lambda parameters, we define a variable and push that, and yeah, then the parameter name, of course. Yeah, we push that parameter. Cool. And then case. Yeah, it returns lambda body to egg on that body. We finish that and we restore the things, and the resulting body, case symbol string, no, that's not needed, is an expression, an egg body is that. Alright. Oh yeah, because then we create the lambda. Exactly, we say body.push. Like outer body.push. So we have body and lambda body. And then in the outer body, we push a lambda containing the lambda body. Something like this. Yeah. We do lose type information right here. So I think this still has to be some sort of special thing, not just in a body, because functions, for example, they also have parents in here. So this should be an egg lambda, I think. Yeah. But an egg lambda just has, body and parameters, like param types, which is a slice of num types. Beautiful. Okay. Yeah, and this really just pushes out an egg lambda, which has the lambda body as its body, and then it has params being the param types, basically. So the param types is a list of num types, and for each, let's just do that inline here. Yeah, we iterate over the parameters 2 times, but I think that's fine. Okay. Yeah. Cool. This call doesn't work because this is a toast type. True, we want to convert that to an egg. We'll just do that, probably not. Oh, yeah. Toast type of toast. Sure. Of toast. Do we have a toast available here? Not really. We have body, which is an egg. Body compiler dot. Nope, we don't have a toast available. Yeah, we should change that. Okay, so where do we do that? The body compiler has, we have a toast in here. And for each function we created toast, code compiler. Yeah, that maybe takes the toast. Yeah, and the egg code compiler contains a toast. Beautiful. Which means that down here we can just pass that in, and then in here we can access that using body.parent.toast. Doesn't work because this is a result. Indeed. Okay, param types is what it's called. Param types. True. Oh god, there are. Let's just print this and fix the print errors, because I'm sure there will be some. And then run that and see what what it produces. Yeah, so if this is, by the way, first we create a tag, then we can switch on that. We have a lambda. Yeah, let's just say lambda. Then the parameters. No. Yeah. Yeah, the lambda parameters, meaning their name and their type. Oh, hang on. No, the lambda has only... They don't have names. Like, they don't really have names. We have only their types. And we print those types. And that's basically it. Yeah, and then for each... then we just print an equal sign, and then we print the body. Kind of like this. Okay. Again, no more immediate errors. Oh, in the yogurt there are errors. Makes sense. Makes total sense. Let's guess. Compiling, yeah, an expression. We need to handle compiling a lambda. That's the first part. And the second part is down here on types. Ooh. That's like actually interesting. We need to check what, like if you call type info on a lambda, we need to do something. Oh yeah, that doesn't make any sense because that is some pseudocode thing. Okay, so this is the idea that this works. And let's also remove that. Yeah. I think this, like, we can actually use this as a comment. You know, we have some to do in the compiler. Let's add that. The type, I think. Yeah. Crazy. Whoa. Oh, yeah, that seems correct. So make incrementer A takes an int, produces a lambda that goes from int to int, and what it does is it just creates a lambda int. Yeah, that takes, let's remove a space there. Yeah, that takes some body and then yeah, references an outer egg ID. That's correct. Yeah, main then calls make incrementer. Okay, so and it assigned that to a variable called inc. And here we just say call inc, because we assume that all calls are calls of global functions, which are not yet resolved, but which depend on the name.
yeah, we'll have to think about how to deal with that. How do you call closures? Well.
Basically, we need to fix the to-dos. Yeah. And this is like, you know, type info to do. I mean, sure, we'll get around to that. But first, the really important one is this. How do we compile Lambda? And I think now it's time to basically copy the commented out part from here and move that over and then implement that. And also probably just copy this somewhere. Array casts, content casts, built-ins, yeah, built-ins, built-ins, built-ins. And then this huge function. Yeah, not sure what to do about this for now, but we'll figure that out. Speaking of figuring things out, figure out which variables the lambda captures, aka the closure, and look those up in the current scope. Yeah. Yeah, we don't need any names in here. That is, oh, that's actually cool. That it's, you know, this to do, for example, resolves itself. Because you will just get an error in the lambda claiming that, I don't know, that A is not defined. Yeah, you know. So that's cool. Yeah, so the names, they don't really matter at all. Oh yeah, and the question is basically, how do we now model lambdas in here? Okay, so I think in the types they are already modeled because we use the same types. In the body, let's see, a yogurt function only has a list of expressions, no types anymore. That's interesting. Oh yeah, because it has a body, and the body has params, which are yogurt IDs, which you can look up here, which give you expressions where you can look up the types, obviously. So you can find out the types of the parameters. Cool. Now we basically want to do the same for closures. Have closures as top-level functions in this map, or like the body of that, basically. Only the body that receives the captured variables. So yogurt op is either a parameter, okay, or only for casting, I think, uninitialized stuff. And then there's comp time stuff, struct member, tag, and switch. And then lambda for creating a new lambda. Yeah, we'll need that. Yogurt lambda. where we basically need the captured variables, which will be yogurt IDs. And we will need a function, or like a we need those, and we need oh yeah, the function the signature is what it's called. Yeah. Yes. Beautiful. Maybe let's even flip those, because I think the function is more important and it determines what it captures. Okay, so we have the function and we have what it captures. Very similar to the yogurt call, by the way. But again, receiver is a weird name, basically. I should update that sometime. Okay, so we can basically create lambdas. That's the idea. And for each lambda expression, we can also check that the captured things line up with what the function expects to be captured. Yeah, but in order to do that, we need for each function also the captured things. Does that make sense? Or do we even need like an enum of this is either just a body or it's a closure that expects captured things? I think we could say okay, maybe should a closure that captures nothing, should that be treated the same as a function that accepts as a function that doesn't expect any should a closure that captures nothing be treated the exact same as a function? And I think not. It should not be, for example, optimized the same way. It still needs to accept this captured thing, because at runtime, if we have a function from int to int, for example, we don't know what kind of function is inside. So we pass it the captured pointer, this void pointer, and see. What do we do here? We could just add a second map for closures. Sounds stupid, but why not, right? We can always unify them later, so I think source actually. No, let's choose something more sensible, like let's say string for now, and I think that's even more horrible, but meh. And that's a yogurt lambda, which is very similar to a function, you know, in that it has expressions and also captured things.
Yeah. Yeah, okay.
Okay. Yeah, let's just go with that. Okay, capture types. Expected the value of the variable. Right. So I guess let's start up here. Captured IDs. Yeah, we don't have any of this. That always works. We don't have any visible things. We will just have to deal with that at some point. Okay, so right. That's also the name of that operation. That's true. What do we do? What do we do? We could put... Yeah, I think it's kind of it's weird that these are separate things, although they are so closely related, and like accessing the expressions and so on will also be very similar. So let's maybe put them in here, but as a maybe. Feels weird, but again, we can always clean things up later and refactor that later. Just want to get some working version first. Yeah, so, oh no, we don't have lambdas anymore. No, we just have functions. That's beautiful. And then in here, when we create a yogurt fun, to yogurt, egg fun, blah, 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 blah. Yeah, really, we just, like, captured is nothing. What was it, slice or yogurt ID or something? Yeah. Oh yeah, for the built-in functions, they also don't capture anything. Like this. And then yogurt fun, the captured field is missing. Compile cast fun. Yeah, true. I should have just copied that field. And same here. Yeah, that doesn't capture anything. Correct. So far, so good. Now, toast.captured variables. What do we do here? Toast is not in scope. Yeah, true. So I think we basically need to check the captured variables of that lambda. Let's see. In the end, we want to create this yogurt expression.lambda, right? With yogurt lambda, which has captured variables and which has a function. And as I noticed earlier, the reasonably ordering would be first the function, then the captured variables. Okay, so here we want to basically go over the expression kind. Now we want to get the captured variables of this expression. Yeah, let's add that. Captured variable of some yogurt expression. Great. Yeah, we'll just create, this is a set, let's say, of yogurt IDs. We can say collect captured. Yeah, I guess. Let's create a list and let's say ignore is a set of yogurt IDs that are fine to use. So collect captured would just call this with ignore and captured. And these are the things we should ignore and the ones that are captured. For a struct we collect, no, hang on, this is on toast, but it really shouldn't even be yogurt, it should be egg expression. list of string. No, yogurt ID. And this also returns yogurt IDs. And then in here we can switch on the expression kind exactly. Let's just see what kinds of expressions there are. There are these. Param, doesn't matter, int, string, struct, but only contains egg IDs, which were defined before. Oh, hang on. No, these are important actually. Yeah, I think I'm gonna have collect captured with egg ID and captured. And what that does is basically it checks is the ID, or like if ignore contains ID, then we do nothing else, aka like this. If we don't ignore that, then we add that to the captured IDs. So captured to push ID, and from now on we want to ignore that. Okay, contains offset. Oh yeah. No, hang on. Oh, egg ID. Yeah, that makes sense. These should all be egg IDs. Does this fit on one line? Yes, it does. Okay. Yeah, nothing to do, nothing to do. Yeah, here we do have something to do. Collect captured. Exactly. Member of collect captured. Beautiful. String struct member symbol. Nothing to do. Exactly. Tag. Need to create that. Symbol. Case tag. I think the tag is a name and arguments, so similar to this actually. Like for each argument and the tag arguments, we want to do that. Okay, and then switch. There's an egg switch, and that actually contains different bodies, doesn't it? Egg switch contains an egg ID, it's the condition. And then it contains cases. Yeah, which is a map of bodies. So this whole visible thing, snapshots, we don't need that. We do need to add the parameters to the ignore set. So ignore dot put param, I think. So switch dot cases is a map, then case dot value is a body, and the body has params. Yeah, and those are IDs. Okay, perfect. And then case body collect those. Okay. And these are not really these, but they are ignore and capture. Okay, yeah. That's the switch. Then we have lambda. Kind of recursive. No, like first of all, no snapshot stuff. For the parameters, we ignore them, so it's very similar to this. But it's lambda dot body dot params,
and then lambda body collect captured. Yeah. And for calls, we do that for the arguments. Call arguments, yeah, that's it. Okay. Nice. Oh yeah, param should be unreachable. Yeah, body is not a field on map entry. True. Oh yeah. Okay, and in here we can say we have some sort of expression. Yeah, I think we should also be able to do that directly on a body. So like collect captured on some egg body. We basically do this. First, for each parameter in the body, we ignore that, and then we collect the captured variables there. Okay, and then in the switch we can simplify stuff because we can just say case.value, which is a body, right? I think so, yeah. It's an egg body. We collect those, and for lambdas, it's very similar. Yeah, lambda body. Collect those. Okay. We can collect variables, I guess. And then up here we can say captured variables gives us egg IDs. And then lambda captures captured. Beautiful. Yeah, and then for each captured ID, we basically want to put that into some sort of struct. Oh yeah, we already know that this exists as a mapping somewhere, right? So like here, we want to map that to yogurt IDs. Yeah. Yes. Captured is expression of captured variables. And then captured egg IDs, maybe. And then the real captured is just yogurt IDs. And so for each argument, hang on, for each ID in captured egg IDs, we basically say, yeah, args dot push compiler lookup ID. Like this. Beautiful. Honestly, that's pretty nice. So args is not in scope. That is unfortunate, but it makes sense because it's called captured. figure out which variables the lambda captures, and look those up. The current scope. Yes. Then compile the lambda body as a standalone function. Takes the closure captured variables as an explicit arguments. So this will be this function takes a yogurt fun builder, yeah, but also a yogurt code compiler. They're somewhat related, right? Yeah, code compiler is like specific to these functions. And the fun builder is just that, yeah. In particular, the yogurt code compiler also contains a reference to the yogurt. So we can say compiler.yogurt .funds .push a new egg fun according to the lambda source something. Param times in body. Well, yeah, true. Some lambda. Captured should also be some. Oh, hang on, just yogurt. Oh, yeah, this can just be that. Oh, almost. And the parameters will be the lambda params is an egg param. Yeah, they don't have names in the egg. That's unfortunate. Let's add names, sure. So an egg lambda actually has params, which will be full-fledged params like for functions. An egg param. Beautiful. And a body. Yeah, and here params will be egg param, and that's gonna be the param dot name and the type. A string and plum type. Sure, no source here. So param types is not a field on egg lambda. It only contains these fields, params and body. So types is not a field. Interesting. Let's fix that. And probably the same. Oh, this works. Oh yeah, that's pretty cool. Okay, and then yeah. Okay. Toast is not a scope. Yeah, because we don't want to do to egg, we want to
Oh yeah, we can just take the type because it is already the correct type. Yeah. And this is the lambda return type. Oh, maybe not. Right, because it's inferred. That makes sense. Yeah, we don't need this, or this, or this. Yeah, we just do other things. So egg. Yeah, nothing of this as well. Hang on, we can just say yogurt.funs push yogurt fun. Yeah. Okay. Yeah. And now we can do this very similarly to how we compile functions in general. Let me check, okay, this is some code. So we compile the body. Check that the return type matches what the function claims it is. Yeah. Let's for now just copy that down here and adjust that. So we don't have a claimed return type. I think it makes sense to build a yogurt fun builder. Build a new compiler, does that make sense? I think so. Yeah, because this function should be compiled independently of all the other functions. So we have a, I don't know, lambda builder and lambda compiler in here. And we just say, hang on. When we compile the call, how do we do that? We say result.fun.toYogurt. Yeah, that's basically like a, I know, we use the compiler, we create a new compiler. Okay, so yogurt code compiler with some egg. The egg is compiler dot egg, I think. Yeah. Code is, I don't even know what. Wait, what is that up here? It's an egg code. Oh, I see. An egg code, and an egg code has the slice of expressions and a body. And I think the egg, the slice of expressions is the important part. We need to be able to get the expressions from that. So compiler.code, I think. Yogurt is compiler.yogurt, and then egg to yogurt. For now, it's just empty. Add to the so we want to add mappings here, egg to yogurt for these. Yeah, the way we do that is, I think inside of the okay, I can do this. We take the expression and that is captured, the ID. Oh, hang on. Yeah, egg ID and then the yogurt ID. And then how do we add a mapping? We should do that down here, right, for the parameters. Yeah, code.body.toYogurt. This, and then we take the lambda body, convert that to yogurt. Oh, yeah, they are all runtime known, right? So I guess, and then compiler.yogurt.funds.push this yogurt fun. Yeah, we don't need. Oh, we need this. We don't need this because we don't claim any return type. The return type is always inferred. So this is not just the claimed return type, it is just the return type. Okay, so this call doesn't work because we take an egg body and a slice. Yeah, we need yogurt parameters, not egg parameters. True. So I guess params is a list of yogurt param. And for each param in the lambda, we just map that to something similar to this, but one abstraction level higher, basically. Do that on the yogurt.
Yeah, params dot
name maybe, and param dot type. I don't know. Oh no, yogurt param is yeah, params. Yeah, it needs a yogurt param dot runtime. For now, these are always runtime. That's easier. Try to create yogurt param dot runtime with egg param. But it needs a plum type. Oh god. Okay. Yeah, true. And that is, oh hang on, that is this, right? Whew, that seems to work. Okay, so then in here, this is not lambda params, but this is params to slice. Okay, okay, the captured field is missing. Yeah, but now we have captured these, so captured initialize that. Now we have a function. Whew. Crazy. Yeah. Okay, then what do we do with the function up here? Here we just say, yeah, we take this function. Oh yeah, and then we just put that into the map. So yogurt.funds.put lambda, and yeah, this needs a nicer name, and the function like this. Oh yeah, this is not yogurt, but compiler.yogurt, I think. Oh. Oh yeah, this needs a yogurt
signature,
which is the name and then arguments, right? Yeah, slice. Nice. Okay. Yogurt expression. Kind. Okay. Does this really work? Toast. This should not work. Where's toast coming from? I think there's just an error somewhere else. And yeah. Yogurt, yeah, doesn't exist. Yogurt expression kind is not a thing, but instead you say yogurt op, right? Yogurt op.lambda. Create a lambda, and we don't have a function because that should be the signature. Well, we can do that. captures.
Whoa.
Okay, and then it needs a type, right? I think that was $. And the type of that is yogurt type, yogurt plum type dot lambda. Are there like helpers or something? Yeah, there were. But yeah, I mean, with a lambda type that contains the arguments in a slice, and that, like, these are the param types. Yeah, okay. Yeah, param types dot push. Beautiful. And the return type, which we have figured out up here from the lambda builder. Yeah. Okay. Okay. Try to assign plum type to field return type. True. Okay. How does it work for other things? Here we push, build out of push before that. In this case, evaluates to nothing, because we take that. Oh, I see. Yeah, just build out a push and return that, which is fine, I think. Okay. Crazy. Yeah. By default, your bit funds capture nothing. Okay. And then up here, you don't handle yogurt opt-out lambda. Indeed, I don't. Yeah, and I think for each captured thing, do something like this. Captures. Okay. And this won't compile because again the next stage, yeah, doesn't work. But that is fine. I just want to see the generated yogurt. Okay. Whew. Interesting. Interesting. Oh man. Oh man. Cementation fault. I mean, I don't even... What? Compiling main int. Okay, compiling make incrementer 2. That seems correct so far. And then we say what do we do here? Yeah, compiling lambda. Let's just output that. And okay, so we compile some sort of lambda. And we create these things but don't use them. Okay, sure. And then we get the capture variables. And this is already something that doesn't work, apparently. That happens here. Captured variables is ignore and captured. Okay, and then we say collect captured on the expression. On the expression means we switch on the kind. Yeah, this is not needed at all. So let's just print collecting yeah, let's say we collect these. Okay. From this lambda. I mean, yes. I see. Yeah, it's kind of unfortunate that this contains the source, which again contains the entire source code as a string. Does it have an ID? Nope. But does it have kind and source? I guess the source should work as well. Yeah, okay, that's the lambda. So what do we do here? We say this is a lambda, so the lambda body dot collect captured. Lambda body is a body.
somehow recursively. Oh, yeah, that makes sense. It does just recursively call itself. So basically for each expression in the body, we want to collect the captured things of that expression. What's going on here? Iter of egg body. Body has expressions, hopefully. Maybe. It does. Nice. Okay. Yeah. Okay, yeah, that's pretty cool. So we collect the captured variables from this closure. And it captures something. So apparently it captures the ID 2. So when we then compile the lambda, ID 2 is not there. That is true. So I think when we compile the body here, at some point we're looking up one of these captured variables, which of course don't exist. Like we need to add them to the mapping here. And we need to think about how they are represented. How do we access these? So let's assume this ends up in some sort of yogurt fun, where captured is, you know, a slice of, I don't know, IDs 0, 1, and 2. Yeah, I think they also need to exist on these expressions here. And I think they can just be params, actually. They are like, you know, implicit params, and they need nothing more than, you know, a type. So they can just be params. How does that work for normal functions, though? Like for normal bodies, maybe. Yeah. Here we just say, for each of these, we say say something like this. That should be fine for this. So let's maybe merge that with our approach. You know, we don't really need our param IDs here. Oh, and these should not be for like the normal params. That should happen for our captured ones. Yeah, so these are yogurt IDs, and then for each of the captured egg IDs, we get that. So captured egg IDs dot get I. That's basically this. And then from the point of view of creating a closure, we do this. You know, we just look up our ID right here. That's correct. And then from the point of view of the closure, we just push something to the Lambda builder, to the internal builder. What do we push there? Well, the params.get. ID. So this would be the get ID, the egg ID. Convert it to an expression. What? Params.get. Now really I just want you know, the parameters, so the like a yogurt up dot param with the type of this. Egg param. Oh, hang on. Nope, that's the yogurt ID. Yeah, that makes sense. So our builder, like, we have, what do we have? A body, I think, a compiler. Get type, something like this, maybe. Or maybe not. Where can we get? Yeah, yogurt fun builder or yogurt body builder. So I think body maybe. Or builder. Yeah, builder probably. Yeah. Yeah. You got fun builder. Yeah, we need that mutably. Look at that. Lambda yogurt ID. Perfect. Yes, that is basically this. And then we do this as well. So lambda compiler add mapping from the egg ID to the yogurt ID inside of the lambda. Yes, of course. And param IDs, yeah, we don't need that because captured is from the point of view of the surrounding function. Hang on, but not here. Oh, yeah, in here, yes, but not in here. So we need two separate. Lambda captured. And in here we say lambda capture push that yogurt ID. Oh, yuck, that's the code is very subtle in these places, I think. Yeah, refactoring that to something easier would make sense, I think. Okay, that's interesting. So okay. So basically in here, when we compile the body, lambda captures 2. Okay. Captures, yeah, clear.
but 2 is not in the map. Why though? Lambda and lambda compiler. Huh. That's maybe to yogurt on a body. Compiling body to yogurt. Mapping. And then we have the compiler egg ID. Yeah, egg to yogurt. It doesn't even get printed. Interesting. Okay, hang on. So down here, say lambda captures this captured egg IDs. Oh, does this fail? But that should not be the case. Lambda captures this. Looking up. Looking at 2. What here? Why doesn't that work? So this is egg to yogurt. Maybe let's see in here. Hang on. Yeah, make increment. So it takes 0. 0 maps to 0. Yeah. Oh. Oh. No, the lambda doesn't even capture 2. It should capture 0. How is that? What? When collecting these IDs, something's going wrong. Yeah, collecting captured from body. Oh yeah, we want to ignore the IDs that are defined, right? Body has params, those should be ignored, true. But also the expressions here, they have IDs somehow. Now let's look at the egg. Has expressions, which is just a list of IDs, and then the egg code. Hang on. Yeah, so really this depends on the egg code. Egg code. And yeah, each of these as well. So like this. Yeah, an ID is, well, that's just that. And for collect captured on a body, we push all of the body parameters and ignore them, and then for each ID in the body expression, we basically say, you know, the expression is code get ID and then code collect captured, and then say ignore dot put ID, something like this. Yeah, this should be the expression. Yeah. And these call themselves recursively, at least for bodies. So they need to pass around those code parts. Yeah, and up here we then call that with the code. Was it compiler.code? I think compiler.code. Oh, okay, so this is interesting. This is pretty cool. What? Yeah, this seems to work. We have a mapping, then we compile plus, and so on. For int and int, also correct. Yeah, and then we are done compiling make incrementer. Right, and this should result in a comp time value. Oh yes, it should. I guess so. Let's maybe I think down here where we create the lambda, you also need to check this kind of thing. Are all of the captured variables comp time known? If so, then we create the lambda at compile time. It's getting complicated, like really complicated. 1,000 lines already, man. Oh yeah. Okay, so we have tags. Well, we also have lambdas, which is yogurt lambda. Value, I don't know. Which contains the captures, other yogurt values, and has a function, which is just a string. Oh, hang on. A yogurt signature. Yeah. Of course. Writing that. Yeah, so this is like, you know, lambda capturing something. and it returns hang on, the important thing is the function. Yeah. Okay. And then true should do that. Struct tag. Yeah, lambdas can't be cast right now. Neither at compile time nor at runtime. Okay, and then when compiling a lambda, we then check are all of the captured things comp time known. So yeah, we compile the lambda body. Is comp time. Yeah, do if what is a builder.get, I think. If that is comp time. And then if it's comp time, then we do something else, we do something else. And the else case is this. Yeah, we can factor out the type. Oh, yeah, there exists comp time. That is not comp time, then comp time is false. Okay, and if this is comp time, then we push the lambda, otherwise that. Okay, and yeah, we can also put that if inside of that, so we always push, you know, like this. We always push something. In the else case, it's this, and in the then case, it's a yogurt dot comp time of a yogurt value. A yogurt value dot lambda. And yogurt value kind dot lambda, something like this, perhaps. Yeah, this doesn't work because it expects a yogurt lambda value. Where captures something and the function being the signature. Okay. Try to assign nothing to field captures. Okay, so yeah, here we can just take the captured things.
and we just push builder dot get capture dot up dot time dot unwrap, and then we return captures dot to slice. Yeah, and I know it's kind of inconsistent when I use captures versus captured. Well, give it up. Oh, I see. So we need parentheses here. Push all this. Dollar type. Yeah. Let's see. True. Okay. Ooh. Yeah, that's true. And we have no way to call a lambda. Oh. But I'm first gonna take a break. Okay, so I think I've figured out a solution, and that is to make local variables basically shadow top-level functions. And that's different to how it works in Martinez, in my previous language. Because here, you know, if you do, where's some good example? Yeah, maybe here. In here, if you do, you can do something like this. I don't know, list is list of 1, 2, 3. Yeah. And list is just a function that accepts 3 items. And there's another list function that accepts 2 items, and so on. You know, but list can be used both as a variable name and as a function. And now the interesting part, if I can do this. Yeah. So every function call always refers to a top-level function. You can never call these variables. And that makes sense because in Martinez there are no closures. Yeah, so it makes sense that basically functions and variables have a separate namespace. But I think in this case, you know, in Plum, it makes sense to kind of merge them together to make local variables over shadow the outer functions. So for example, ink, if we see a call of ink, we would first look for a local variable named ink, and only if that doesn't exist, then we say, okay, then there's got to be some function call, and basically let the next stage, let the what comes after the egg, the yogurt, let the yogurt figure out which function is called. Yeah, it makes this kind of pattern not possible, but I think that's fine. Like in this example here, for example, it would be weird if this would call the global function. Oh man. Yeah. And we could somehow alleviate this maybe. Like if we really wanted to, we could kind of avoid that problem, or like support different namespaces there. For example, we could check if the type of this is lambda, it's a function. Then, only then is this the local function that is called. Otherwise, it's some global function. But that's kind of weird, because then what if
I don't know, what if you do this, you know, yeah, maybe not, but maybe. So we have some function foo, which takes bloop of any t, for example, and then it has something like this in here. It would be super, super weird if, you know, if this function is called with a closure, that it would then call the closure, but for all the other cases it would call this global function. That's, no, we don't want that. That is cursed. So we don't want, you know, like local types to override the available functions there. But we also don't want it the other way around. We don't want, you know, if you have this and this happily works, and then like even if this is a closure from like int to int, let's say you do this, then like thousands of lines in between, and then you have some other function that you are working on, and here you say something like bloop, and the tooling is like, oh yeah, bloop doesn't exist, do you want to import that? And then you import bloop, which means that like at the top of the file, I don't know how that's gonna look, you know, but bloop is imported. Then you don't want this meaning here to change. So these top level functions, they should not take priority over over closures. So if something is a closure and it looks like you call that, this should always call the closure. But at the same time, the local closures, it would be cursed if, depending on their type, they override global functions. So I think the same thing here is to just say that, hey, local, you can't use a local variable name and also call a function with that same name afterwards. You have to either rename your variable or rename your top level function, which I think is a fair choice. Okay, so yeah, let's remove this and let's just go to the egg, I think. Yeah. In the egg, we have this call, but we also want some sort of lambda call, which will just be similar. Egg lambda call. Yeah. Struct egg lambda call with a receiver. Yeah, and in this case, let's call it lambda maybe, which would just be an egg ID, something that is defined previously in this function, basically like a local variable, a value. And then we also have the arguments similar to a normal call. Yeah, that's basically the idea. Yeah, it turns out calls and lambdas don't really have anything to do with each other, so yeah, let's leave it like this, I guess. Okay, and that means that calls, like lambda calls, will look pretty similar. Call, and then instead of having this string, we just say call.lambda, and that's just some ID, and then we have the arguments. Beautiful. Okay. Yeah, and then in the name resolving, wherever that was, like in the call, yeah, here in the call, we check what's the kind of this. And if it's a name, then we don't just want to push an egg call, but instead if we basically do a lookup, just like here. to switch on that, then yeah. If we have some local thing, then this is gonna be a lambda call of that local. Hang on, egg lambda call. Lambda is local, and yeah, maybe let's call it lambda. And the args, of course. Otherwise, name receiver, name. Let me call it name, why not? And yeah, I guess this. Okay, yeah, and this should also be fine. So maybe let's say otherwise. Yes, the default is just some lambda call. Like, the default is that. And then later on we can still have an error, like, hey, you have a call of something that is not a function when we compile the lambda call. Okay, and here the lambda will just be the call receiver. Okay. Oh yeah, call receiver is here that was mapped to an ID. Here it wasn't, so here we need to compile that actually. That makes sense. So lambda is, what is it? Call.receiver dot to egg body visible. Beautiful. And then egg lambda call of that lambda. So far so good. And we want to push that to the body using our toast source. Yeah, okay, that seems fine. Although I think, yeah, the pushing, let's do the pushing outside of that. So let's do body.push of this, and then in here we don't need to have this thingy with the same source everywhere. We just have this. I don't handle toast expression of int. Oh yeah, because switch in the switch is kind of weird. Nice. So let's just check what happens. Yeah, exactly. So in the yogurt, we have a lambda, we have a call, and we have a lambda call. Yeah, I guess let's just copy all of that, because of course. Yeah, lambda call is not this. No. Lambda is call.lambda, that is like a already compiled function. Oh, we should check that, by the way. I think you should not be able to create, like you should be able to create yeah, basically you shouldn't create a function that itself is generic then, you know. You shouldn't be able to create something that you can then call with, I don't know, 5 and a string. Like inc5 or inc hello. Like, I think lambdas should always work on concrete types. They're like values you can pass around and so on. Okay, which means we don't need to compile anything. You know, yeah, we can look up. Oh yeah, we don't need to look up a function, we just have the value. We don't need to compile anything because it's already compiled. We don't... the return type might be useful. Well, yeah, maybe. So call that lambda. Then we have arguments, yeah, which is a list of yogurt ID, and argparams, which is a list of yogurt param. Yeah. So if this is lambda call, yeah, we have the lambda, and the return type is not this. It's just lambda dot like compiler dot lookup lambda. Oh, sorry, builder dot get lambda dot type dot lambda, maybe. If comp time result, then something. Hey, body dot push call. Yeah, this is more like a lambda call, I think. Which doesn't exist right now, yeah. And like in general, the comp time thing, we will figure that out later. First, let's just compile this to a lambda call. But the lambda is, well, the lambda. And we figured out the type here. Well, not quite. We need to ensure the type matches. Args is yogurt ID. Yeah, we don't need the params anywhere. No, not really. No. I mean, here we can just say call.args do if, not builder.get arg.up is comp time, we can do something like this. And then we don't need the arg params, so we don't need this, we don't need this. Question is, do we need the args? We kind of do. Yeah, okay. Yeah. We do need those. But we don't need the type. So here we can just say, hey, let's inline this, and inline this, and inline this, and look at that. We have the lambda, we have the arguments. Now we want to make sure arg types match the lambda type. Yeah, so here we have the lambda type. Dot type that needs to be lambda, or we return an error. Where do we do that? Return error of yogurt ID error of error called non-lambda. And then the type, and the source would be I'm not sure. Call dot, does it have source or something? Or is there like, there's an expression. Hopefully expression has a source. Well, let's see. Okay, so we have the lambda type, and then for both in zip the actual arguments, so args, and the lambda type args. What we do is basically actual type is both dot a, like hang on, and builder.get both .a .type, and the expected type is builder.get both .b .type. Yeah, and now we need to make sure that they are the same type. So actual type equals expected type, and yeah, this is very strict. Maybe we can cast things as necessary, I don't know. Yeah, or we're gonna return an error, similar to what we do up there. Lambda expects expected type got the actual type. Yeah. Okay. And then, yeah, we check that the types match. Next, we find out the return type, which is just lambda type dot return type. Beautiful. Yeah, we check if all arguments are comp time known, which we ignore for now, and then this will have the return type. Beautiful. Okay. Yeah, collect captured on a lambda call. I mean, the call lambda dot
the arguments. This does not work because it's an egg ID, and that doesn't need or want the code. True. And then up here we say builder.get. Oh, lambda is true. We want to look up the corresponding yogurt ID. Okay, then in here, no. Get yogurt fun, build a plum type. Hang on. Lambda type.args. Oh yeah, those are already types. I did not realize that. Egg ID. Yeah, but we can just use args. Beautiful. Comp time result is just that. Yeah, lambda call is yogurt lambda call, I guess, with lambda and arguments. And that probably doesn't exist. And it doesn't complain, so lambda call is yogurt lambda call, and yogurt lambda call is very similar to a yogurt call, except you call a concrete value instead of some global function. Okay, so return type should be dereferenced. Sure. Huh. Yeah, that is true. Does that work? Yes, it does. Okay. Yeah, writing that, I mean, sure. We can do that. Writing a lambda call. Well, paste the lambda call. We write the lambda. And we write the arguments. Perfect. You don't handle yogurt of the lambda call. Indeed. Indeed I don't. Yeah, we can't call lambdas yet. And that is exactly what we want. Whoa. Okay, so it compiles. Oh man, look at this. What? Damn. This is crazy stuff. Okay, so matchings, yeah, I don't know what's going on here, but then instruction crash. Interesting. Oh. Yeah. Yeah, where do we say that value should be comp time known? Yeah. And the call. Okay. I mean, yes. return value of, and then maybe the function, or like the I mean, yes, the crash built-in, even if that's called with comp time arguments, it doesn't evaluate to a comp time value because it crashes. It's supposed to, it needs to do something at runtime. That's like, I have another idea for like how to reorganize the comp time thing. Maybe I'll do that later. So return value of, yeah, I mean, it is pretty obvious like what's going on here, but like this is the unreachable built-in or something, right? Yeah, return value of built-in crash. Yeah, I think I'm going to do that here. Oh, hang on. Call ID and then return expression is this, blah, 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 blah. Yeah, and we just switch on that. And if that's some value, then we're good to go. Else, like, yeah, we just actually push the call and we build a push the comp time value. Otherwise, we just print a warning, hey, this should be comp time known, but we still evaluate to the call ID. I don't, okay. Indeed, I don't. Oh yeah, because this, we can just do that. Indeed. Yeah, I think diff doesn't really exist. Instead, oh, I see what's going on here. Oh, this is being evaluated at compile time. That's why. I see. Yeah, that's cool. Yeah, all of these can be replaced by an actual divide thingy. Not what I wanted to do. I wanted to go here. Not literally all of the diffs. Yeah. Okay. Yeah. I'm interested in how this is gonna look. Okay, so. Oh, I see. Yeah, let's maybe undo the right adjustment. Yeah, and here let's see why I did that manually. Sure.
Okay, so let's maybe look at the main function, which is somewhere. Not here. Oh, here. Okay, so look at this. We have a comp time 2. Then we call make incrementer of 2. Make incrementer then is, well, is somewhere here. Make incrementer 2. Just creates a comp time lambda capturing 2, the value 2, with the name some lambda. I mean, that's, yeah, not correct. You can only have one lambda in your code currently, otherwise there will be conflicts. Yeah, but that lambda just calls plus. Oh, look at that. Yeah, using 0 and 1, and 0 is captured. I mean, yeah, we should print the captured things here as well, I guess. But fair enough, so we have this lambda, and because that call works at comp time, really it's just, converted to a comp time expression, I guess. Yeah, comp time some lambda. That is quite beautiful. And then we have comp time 5, which, sure. And then we call that lambda with 5. Oh, that makes sense. We call that lambda with 5. And that, that results in some int, and then we call to a string on that. Seems reasonable to me. Very reasonable, actually. Okay, yeah. So then let's go to the next stage. Compiling to bytecode. Yogurt, and then we have this universe thing, where we also have to-dos. Two to-dos for the expressions, and another to-do down here for converting things to an actual VM object. So I think lambdas are a new kind of object, right? Lambda is, I don't know, some lambda object. And let's maybe put it like this. So a lambda object has a lambda, which is, it's basically a function, so it's it has the code where it's from, the code object, and then the function ID of the lambda, of the function index in here. Yeah, and then it has the captured variables, which is basically a slice of objects. Mm-hmm. Yeah. I think it makes sense to have a separate object for the closure now. So the actual like variables, like maybe not. I'm not sure. Yeah, let's just keep it for now, like this. Okay. We have a lambda, and then we can. Oh, we need new instructions as well. Basically, for creating a lambda. What does that do? Basically, we need a function ID in here, as well as the number of captured variables, right? So function and number of captured variables. Beautiful. And then we there should be some errors in here somewhere where things don't handle these. Oh, in the VM. Yeah, I guess that makes sense. Right. So for the lambda instruction, fun and captured, what does it do? It basically pops, like, let's first get the function, Function is just fun and captured dot a. Num captured, is fun and captured dot b. And then very similar to the call or the struct, the struct here. We pop the items off the stack. Initial slice of objects with num captured length, and for each captured, or like thing we want to capture, we basically set one of these in the captured list to that. So basically we now have a slice of object IDs. Exactly those IDs which are captured. And that means that this instruction also consumes consumes the given, number of variables. Consumes num captured, pushes a number. Okay, so case lambda, we do this. Then basically we want to create a new lambda object. So something very similar to what we do up here actually, except it's going to be a lambda with code, which is the current code, with a fun, which will be, well, the fun right here,
and the captured things will be the slice. Yeah, the function field is missing because let's call that fun. Just so it's, you know, consistent with this and so on. Yeah, fun. Beautiful. Okay. And then when we write those values, we actually like print the capturing, and then for each closed over thing. So for capture in lambda.captured do writer.capture, and then we do lambda.code, which I hope is just an object ID, probably, and lambda.fun, which is the function index. Okay. Yeah, I think it makes sense to put those at the beginning, actually, like this. Yeah. Okay, so then writing instructions, sure. Lambda plus and then for all of the arguments, oh no, we can say with lambda dot, oh I see, A and B, yeah, captured. And the other instruction, I'm not sure what that was. Hang on. Yeah, okay. Why did we only add a lambda instruction? Yeah, we did. Do we need a lambda call instruction? Maybe not. Oh yeah, we do. So pops a lambda from the stack, pops its number of args, pushes captured things, args, and then yeah. Okay. So expected the type of the variant. What's here? Yeah, it doesn't have any data. And that should mean that in here we have a lambda call. Yeah, converting a lambda to an object just means creating a new object dot lambda. With a lambda object, which contains code, which I'm not sure what to do about that. Yeah, no, this will be a bit more complicated. So first, similar to what we do here, we need to instantiate the captured things. Of that lambda. Lambda.captured, is it that? And yeah, here we have the code. The actual fun is the lambda.fun, I think. And then, yeah, something like this. Captured is not a field. Captures. That's inconsistent code. Right, so we need, when converting something to an object. Which we do up here. We need to know the code, an ID for the code. So this returns fun code. Yeah, here we say universe.new. And I think here we need to do like a placeholder thing. Yeah. Universe.new object dot and that's just placeholder, and then we say universe dot get code is that get ref probably. Yeah, so then because we now know the, yeah. Because we know the object ID of the object that is being compiled in here, yeah. When we compile the function, we can pass the signature, yeah, but also the code in the universe. So the signature, then the code, which will just be an object ID, the universe, and the signature. Okay. And then in here we could say function body compile with instructions and the stack and the fun and the code. And the universe and the signature to ID mapping. And then down here where we say to object with this universe and this code returns a new object ID, and we have the code. That means, of course, that we need to pass the code to recursive calls as well. And up here, we need to pass on the code too. Okay. So what's going on here? Lambda.fun is not a field, it contains function. Damn it. Yeah, that's a fun ID, and that means that we need that mapping. We need the mapping that we use for calls. Here's signature to ID. We need that down here as well. Try to assign yogurt's signature to fun or fun ID. Yeah, because in here we can now do, signature to ID dot get that function, giving us a concrete thing, and then captured needs to be a slice. So captured to slice. And up here we have case value compile. It's going on here. Compile yogurt body list yogurt fun. Code. Nice. Okay. Then the VM calling a lambda. Yeah, it just pops the function. The lambda is VM dot pop boom, and then we're gonna pop all of the captured things actually, which is a bit cursed, but I guess that's fine. That's just lambda dot captured. Oh no, hang on, we're gonna pop the amount of arguments, yeah. Oh, okay, so the fun is actually, what do we do with call? Yeah, this is right here. Current, no, not current call, but lambda call dot code. Lambda.call .code, yeah. Oh yeah, this is guaranteed to be a lambda. Yeah, then we have the code, and then we have vm.get of that is guaranteed to be a lambda, unwrap. Then we get the code of the lambda, the captured things of the lambda, and then we say uninitialized slice for some reason. Oh yeah, because we want to get the arguments, kind of like we do here. Yeah, and this, like, the number of arguments is just, code is that. Code is an object which we can get, which is guaranteed to be code, which has functions where we can get lambda.fun, which is a fun ID. We can probably get that on the code directly, I think. Yeah, and now we have a real function where we can say the function has parameters. doesn't. It doesn't have parameters. Only the name and instructions. Well, the Lambda could say it has this many parameters. No, but really that should be obvious from this, actually. Yeah, so we don't need to do that. We just pop the number of arguments. Oh yeah, I see. Lambda call takes, pops a lambda from the stack, pops contains num args, pops a lambda from the stack, pops args, pushes capture args, calls to fun start. Okay, yeah. Okay. Yeah, we pop all of these off the stack. Hang on, we can say list object ID, yeah, and then just say, that's easier, list dot push, like args dot push, and yeah, that's the reverse order, but that's fine. Maybe, yeah, make it obvious. Yeah, and then for each of the captured arguments, so for captured in num args, I think, what we do is we basically what do we do? We basically take the, we push them, right? So vm dot push, and this is like the lambda captures, and the individual capture things are pushed to the stack. And then the arguments, so for arg in ref, no. Yeah, vm dot push ref args dot pop a break. List does not work. Okay, yeah, true. Oh shit, pop is, oh, I guess, oh, is there a pop? Oh, pop maybe? No, there was not. Oh, yeah, let's do that. Oh, fuck it, let's do it like this. Not super elegant, but I guess that works. And then we can just say for arg in args do vm dot push arg. Okay. Now we have pushed the captured things, we have pushed the argument. It is time to actually call that lambda, and that works like this. So vm.callStack.push entry, and the code is vm lambda.code. The function is lambda.fun, and we start at the beginning. Yeah, so the calling convention for lambdas is basically push all of the captured variables on the stack, then all of the arguments, and then that should work. Okay. I'm just wondering what's going on with the function here. Oh, right. So for functions, when we compile functions, hang on. Yeah, we can call a function. I mean, that's sure, we can do that. Oh yeah, when we compile functions here, we want to also compile the captured thing. Like, you know, if function capture, if fun.capture is captured is some captured, yeah, basically that. Oh, those also need to be popped at the end. Which means we basically need to do this again down here. Was it something like this? Push and below top. Beautiful. Beautiful. Okay. What? I think that's temporary. Yeah, exactly. Okay. Okay, so where are to-dos? Right, if we want to create a lambda, what we get here is what exactly? Well, it is a tuple. Oh, hang on, no, we are compiling like the yogurt. So we have a yogurt lambda. Yeah, and what we do here is we
push all of the captured things, then all of the arguments like we do here. Oh, hang on. No, only not the arguments. No, only the captured things. Yeah. Yeah, okay. I think then we just, push something like that. Yeah, we should also do this. Like function is signature to ID of the lambda function, and then we push the lambda instruction, which needs a function and the number of captures. Yeah. And that pops some things. And it also pushes the call itself. But hang on, I think that's done. Yeah, that's done down here. Yeah, I think that's it. And that was something. Okay, and then the actual lambda call would mean that we push all of the arguments. It's very similar to a call, actually, I think. Yeah, we push all of the arguments. We push the lambda. Let's call it this. Yeah. Lambda call. Hang on. Lambda call. Yeah, I know. What does it have? You got a lambda call with a lambda. Oh yeah. So we also want the lambda to be there. So instructions.push, bytecode instruction push from stack the call.lambda. We have that. And then we push a lambda instruction, which I think needs the function and no, which just needs, oh yeah, it does need the function, right? Not sure. No, calling a lambda just means we don't have a function in here. We push the number of arguments, yeah. We push lambda call with call.args.lambda, yeah. And what that does is it pushes args.len plus 1, and then it pushes the result. yeah, that's basically what we do down below.
Oh well. Oh, interesting calling. Does unwrap.
I think I'm gonna take a break and then continue. All right. Compiling to bytecode and called none.unwrap. That is not good. Not good. Can we do more debugging in the bytecode? Probably, right? So I know we had some VM debug calls in here. So let's maybe print the VM. Why not? So data stack 5. Maybe printing the instruction helps. I want data stack 5 and then call stack empty, called none.unwrap. Well, we don't even have a single instruction here that we can see. Probably this right here. Current call. What is going on here? Code.unwrap, probably this one. Oh wait, when we I think when we compile our code, we now have this temporary thing up here. Where's that here? Oh no. Here. Yeah. This is not valid. Like, we need to get a reference to the underlying thing. So universe get code. Universe has objects. So let's do something hacky. Let's say universe.object get ref code.int, and that should be the object.code. Yeah. Because we put a placeholder in there and then nothing worked. Oh damn, that looks correct. Let's see if this actually did what it was supposed to do. And there is a lot happening here, apparently. A lot. Yeah. Can we like simplify that? Okay, so what I want to do is, okay, it is pretty simple actually. I mean, yeah, that toString is, let's just return high instead, I guess. But it doesn't need to be a string, right? You can return anything. So let's just return that. Hang on, plum. Yeah, here we run that. Yeah, that's just any object. I can return any object. Oh, we may have to like adjust the type. Yeah. So the actual return type now is int, which is fine. Okay. Yeah, much more manageable. Okay, so compiling bytecode and then running. So we have a 5 in here. We push object IDs 1. Okay, sure. That is the 2 apparently. And now the call stack. Yeah, next instruction basically. Running push from stack, pushing the 2, and then calling. This is make incrementer. Yeah, we see that here. So the call stack now contains make incrementer, which means push object. Damn. So now there's a function capturing something. Oh, hang on. That's actually, yeah, I mean that seems correct. Yeah. What? What? Okay, so this has object number 0, which is the code. Function number 4, I mean, sure. And it captures object number 5, whatever that is. But that's fine. Crazy. Yeah. And then we push that same thing here. Run pop and below. Then we return, so now we're back in main. We have 5, we have 2, and we have our nice closure. And then we have this closure. We push the 5. Yeah, push all the arguments, makes sense, yeah. And then what we do is, oh yeah, pushing the closure again is because we assign that to something, I think. Maybe. Yeah, now we want to call that closure. So we push the arguments and the closure itself. Then have lambda call with 1 argument, which means now we're in some lambda. There. And you can see that the captured variable, the 2, wherever that was. Yeah. This is now on the stack, below the actual arguments, the 5. What? And yeah, they push things into crazy stuff and everything works. What? I mean, that's pretty cool, right? We support closures. This works. That's crazy. Okay, cool. Very cool. Or can we also print the universe, maybe? Print maybe we can do that. We can't yet. In here, when printing, we should handle Lambdas. Of course we should. And what we should do is print backslash, then the lambda code, lambda fun, and then capturing, and then for capture and lambda capture, do printing the capture, and then we print the closing thingies. Captured, yes. Okay. Okay, yeah, these are the objects. We have object 0, which is the compiled code. Pretty cool. We have object 1, which is a 2, object 2, which is also a 2, object 3, which is this closure, I'm sure. Then object 4, which is a 5. Object 5, which is a 2. And you can see that these closures, they capture the 2 that was in the environment when they were created. Yeah, and then the result is 7 also exists. That's amazing. Like, honestly, that is super cool. Right. I guess, what to do next? Yeah, let's first commit this, and then we'll see. Yeah, committing stuff. Yeah, we've changed a lot of things. Yeah, and here we have, yeah, maybe we don't need that, you know. Damn, so much code. Okay, yeah. Support Lambdas. Yeah, not the Rust code, maybe. Cool. Yeah, I guess let's do some much needed refactoring. Much needed. Yeah. And I mean, closures don't work perfectly because we can only have one closure because it's named some lambda, you know. But I really want to get to refactoring. So yeah, fixing closures is, well, we'll do that later. Okay, so the bacon is fine, I think. Like, I'm just focusing on like code quality and doing stuff, you know. Yeah, bacon is pretty readable, I think. Then next step is toast. And here I have some improvement ideas. So one is, you know, this. We should move this closer to the original source code. And then not save the source in every tree node, but only in the leaves. I think that makes things cleaner. And like actually shorter, probably. Let's see, 840 lines. We'll see where we end up. So we have the toast with definitions. Definitions can be a type definition or toast fun. Yeah, and a type definition. Well, why is toast fun only called toast fun and toast type def has a def at the end? That's kind of weird. But I guess it makes sense in the you know, it's toast type would be a better name, I think. But toast type is already this. Like naming a type or referencing a type. And I think that's like the main thing you do. So having toast type be that is fine, I think. And also def is already already here. So type can have a name, yeah, which contains a source, very neat. And then it has parameters, which is a slice. Oh yeah, it's the definition. So on the left side of the equal sign, name and parameters. On the right side, a type. Yeah. For a variable, type variable, we have the string and the source. Makes sense. The call has also a name called string and source and toast types as arguments. A struct just has a list of fields. Yeah, okay, but that makes sense, I think. Which have a name and a type. Hang on. Yeah, let's not make this lists, it turns into slices. Toast type field and toast type case for enums. Enum has cases. Case or variant is the question. Usually, I think they're called variants. Like in Rust, they are called variants. Enum variant, enum case. I think it makes sense to, in the switch, for example, a switch has cases, branches, cases, I think. And for enums, let's call them variants. So let's just rename this everywhere. Toast type case to toast type variant, like this. Okay. Enum has variants. Makes sense. Those have a name and kind of multiple arguments. Yes, and lambdas is toast type lambda. Has arguments and a return type. Okay, nice. Now toast fun has a name and has parameters. Which are just a name and a type. And it has a return type, which is a toast type. And a body, which is a toast expression, which has a source. And let's not do this. Let's say this is a toast expression. And I know at some point we refactored it the other way around, but especially like now we have string and source in so many places in here. So I think like you can get the source from toast expression by just traversing down and looking into, I don't know where this int comes from, for example. I think the int should have a source, for example. Yeah. And string, maybe, no. Yeah, let's say int is a toast int. And sure, it has an int, but also a source. So this is int and source, and this is string and source. Symbol as well, string and source. Name is string and source. Put the sources everywhere. Yeah, struct has toast fields. Which have a name, yeah, the toast expression also makes sense. Yeah, and then the field. Yeah, toast members are of some expression and they have a name. A symbol, string and source. A switch is a toast switch. has condition and cases. Yeah, now case, the name case makes sense. Yeah, name, okay, sure. Yeah, then lambda is toast lambda with parameters. And a body, toast expression. Okay. Call is a toast call with a receiver being any toast expression. Yeah, and arguments. A slice of toast expressions, cool. And now toast var is, it has a name. Yeah, let's turn that into a name and source. And it has a value. Okay, yeah. And maybe that's string and source. Yeah, it doesn't make sense to have like an int and source instead of this and having int and source here, but oh. Yeah, let's do that. Int and source with an int and a source instead of this. Okay. Yeah, this doesn't really need to exist anymore. And here we have two variants. We have int and source and we have string and source. Beautiful. Okay, yeah, then we can write toast. True. So we go over the definitions, and if it's a type definition, then reprint the name equals the type and the parameters in between. Yeah, that makes sense. Yeah, if it's a function, we print the function name and the parameters as well as the types. Arrow return type equal, can do it like this, and then the function body. Okay, then writing a type, that's actually interesting. Yeah, I think I want this writing to not have parentheses when they are not needed. Yeah. So I think I'm gonna add another function like write, I don't know, without white space or something. Yeah. Could even, yeah, let's create a struct without white space. And it's generic over T, and it's just called like format without white space maybe. And you can create that by calling this function without white space of some T. Very simple. It just returns a format without white space of that value. And the cool thing is the write method for this format without whitespace thing of some t is not implemented by default. I think we'll need that in other compiler stages as well. Does it make sense to have a utils ordner or something? A folder? I think not really, but yeah, okay. Let's maybe put that. I mean, for now, let's just, for now especially, yeah, let's browse and toast, right? Okay, yeah. So we have this struct, and that allows us to implement type format without whitespace toast type differently. So in here we will need to add parentheses when needed. And this will just assume it's fine to have this not be surrounded by parentheses and have whitespace in the type. So for a call, we don't need parentheses. We just put the name followed by the arguments space separated. For the struct, we just have the and symbol and then the fields, consisting of the name and the field type, but this here no spaces are allowed in the type. So now we can just say type without whitespace, and when this will be converted to a string, it will call this this write method down here, and put parentheses there if they are needed. Okay, yeah. Same for the variance. Like this should be pretty similar. Oh. Yeah, I think we always need parentheses if there are arguments. So if variant.args is not empty, yeah, I guess writer space, we do that all the time. And then if there are yeah, okay. If there are okay, we print the name and then the arguments. They are not allowed to have space, to have white space. So arguments without white space. And if there are no arguments, then they are empty. So then we won't print parentheses. Yeah, that makes sense. Okay, for lambda we just print backtick thingy, and then the argument types without whitespace, mapping to the return type without whitespace. Yeah, formatting without whitespace. For variable, it's the same as formatting the variable with whitespace. So out here, type.value is it in here? Yeah, for calls, no, calls always need parentheses, so this will just be that. Boom. Structs also always need parentheses. So also, like, this is called fields sometimes, and sometimes I'm just gonna call it struct. I think that's the more reasonable thing to do. Same for enum. And for lambda as well, yeah. Only variables don't need parentheses. Makes sense, I guess. Okay, then writing a body with some indentation. Sure. Means writing an expression with indentation, and that means yeah, some of these are like really kind of weird. So I think let's do I want like print like indentation? I want indentation printing, right? Like general indentation printing. Yeah. Struct indentation just has an amount, and then fun indentation takes an amount. Oops. Amount int returns indentation. Yeah, and that just returns an indentation with that amount. Yeah, let's omit that here. But then writing that indentation means exactly this. You always write 2 spaces. Yeah, you know what, let's maybe move these into a separate, I don't know, formatting. Yeah, why not formatting? Okay, so annotation stuff, and also what else was there? Yeah, white space. Beautiful. Okay, yeah. Ooh, hang on. Even better. I think we can just print, you know, and then kind of wrap a value in indentation and then print that, maybe. Maybe, yeah. I mean, this should be like pretty readable. It should be like the source code, and currently it is not. So here we write indentation of our indentation. Okay. Then we have yeah, we could do something like this. Yeah, and then even have a function, I don't know, indent, like inc for increment, yeah. And that returns a new indentation. Yeah. Let's do it like this. And then we can actually like pass down indentation here. Like instead of an int, just pass indentation. And then we can just print that. What? That is kind of crazy. Yeah, and the int has an int. The string has a string in here. I think we should just use the debug string because who knows what is in there. Yeah, for a struct. Oh yeah. We print the fields like this, field name, and then indentation dot inc2. Oh, let's do it like this. Yeah. Struct. Oh yeah, and again, let's call this struct. If a struct is empty, we just print an ampersand. Yeah, I guess that makes some amount of sense. Sure. Yeah, a member doesn't print member, no, it just prints the member of and the string. Inc is kind of bad. Let's instead implement plus. Yeah, then here we can have indentation plus 2, and here indentation plus 1. Beautiful. So we have that dot and the thing. Okay, then symbol. Just prints the symbol. That seems correct. Almost. And yeah, switch prints the condition. And then similar to this right here. Yeah, where we just print don't print that, but instead we print that. Yeah. So if it's the first one, then the %, otherwise just indentation. And then here we have the case, like this part basically. Yeah, and oh yeah, this is also important. That we could just say writer write indentation. Crazy. Yeah. And then the body with indentation +2. Cool. Then writing a name is straightforward. Okay. Writing a lambda, well, we have this, correct. Then I think we can just write the param. That already does that. And then an equal sign and a new line, yeah, that makes sense. A call is not like this, no, it's just write the receiver of the call. Yeah. And then call.args. Oh, I see. Yeah. Yeah, let's do it like this, I guess. And also we don't need, I think this is the wrong approach. Let's do this per expression down here. And an expression is, it doesn't need to print indentation at the beginning, I think. Just every time it creates a new line, it should then add more indentation afterwards. At the correct amount. Or does it? Yeah, I think so. Okay, strings. Yeah, this also makes sense. No, not quite, actually. Yeah, let's say each expression has its own line, basically. So here we have indentation. We print the indentation and then the end. For the string, we print the indentation and then a string. For a struct, we print for each field the indentation and then the field name, and then in a new line, the value. That makes sense. Whereas if the struct is empty, we just print the indentation and the end. For a member, we just print the member off without extra indentation. Yeah. And then in a new line, aka like this, the member name. Perfect. And it is not valid code, to be honest, like having the dot something on the new line with without indentation, but I think it's fine for now. We may even want to allow that. Not sure. Okay, yeah, switch. Condition, no, not indentation +1, just directly that. And then a new line, and then printing stuff. And I think we also need, new lines here. So new line before that. And when writing the body, this doesn't itself print a new line at the end. exactly. So we need to, in the next case, print a new line. Okay, makes sense. Then name prints indentation. Lambda just prints indentation, and then the parameters on the same line, new line, and then the body with indentation +1. Okay. The call prints the receiver with the indentation, perfect, and then the arguments with new lines in between. Where's that? Where's writing? Oh, here, writing a slice of toast expression. Okay, yeah, prints, perfect, prints new lines in between them. That's exactly what I want. Okay, yeah, these are just the arguments with annotation in between. Perfect. Oh yeah, we should print a new line here. Variable just prints name equals with annotation in the beginning, and then the actual value with annotation +1. Perfect. And this just prints the body, aka the slice. Great. That's more reasonable. Then, oh yeah, the entire parsing and so on. Yeah. Maybe let's first simplify this. Toast type.struct. Try to create that, but it needs a slice. Indeed. Yeah, toast expression kind. Let's just replace that with toast expression, because toast expression kind doesn't exist anymore. What's going on here? Toast expression.int. Beautiful. Needs int and source. Indeed. Yeah. Here you go. Actually, I think the start. Yeah, the start is kind of hacky. Let's not do that. Let's say parse string and parse int. They return the source as well. Yeah, so this returns maybe of string and source. Like this is the actual start, including quote. Then we consume the quote and we start our actual string. The parser is at the end, then this is a bad string. Indeed. Indeed. Yes, otherwise if the current thing is that, then we break. If the current thing is that we break, otherwise we advance. Oh, because consume also consumes white space, right? Does it? Where's the consume even defined? Consumes white space. Yeah, okay, so that's why we don't call consume this, but instead we say current is this, then break. Okay, fair. Very, very fair. And then we advance. Fine, then we have the end. We consume this. We have the end including quote is parser cursor, and then we take the input substring of this add, and then the source, which is parser.source of maybe start including quote until end including quote. Yeah, and I think I don't want to indent this. It already is kind of indented, you know, so I think prefix operators don't even exist. I think this is fine. Yeah, I like that. And then again, maybe that's clearer. Yeah, let's do that. Okay, very nice. Then parse identifier, parse name, parse symbol, parse atom, parse string. This is not needed anymore. Parse string just returns a string that already contains a source. Yeah, and this can just be that without any extra headache. Beautiful. Then in here, the int parse int, where's that defined? I would have thought it was further up, somewhere here. Parse string, but here's, oh, interesting. Yeah, no, let's maybe put that. That is not like a helper function like this, you know. This is like actually useful function. Okay, so start. We have the start, and then we have the end, which is the parser cursor. And then if start is end, then return none. Otherwise, return none at parser the source of start to end. Beautiful. And yeah, that means that this returns an int and source. Crazy. And then, yeah, this seems nice. Yeah, and this would just be the int that already contains the source. You can even do this. Look at that. Like, that is readable code. Nice. Huh. Compact. You have nice. Yeah, you can visually parse that really well. Just compare this to this. The difference is crazy. Okay, yeah. So we have that. Let's maybe first fix all of the errors here. Yeah, the member doesn't need a source anymore, because even the source just goes from the expression to the name. Like, you can calculate that on demand if you want to. Yeah, basically all of the add things are no longer needed. Same here, the body source, I think. Yeah, just create a body, and that's it. Yeah. Yeah, the backslash source is no longer in here. So we might want to actually add something to the toast number, let's say. Rather than adding a generic source to each node, we should add like backslash to the toast lambda. That the toast is entirely a syntax thing, you know. Yeah, right. This is not needed. All this. Beautiful. And then we have these piped into .kind. This is not a variant of toast expression. True. We just do that. Don't need this. Beautiful. Not needed, not needed, not needed, not needed. Well, let's keep this. Yeah. But look how much nicer things become. Okay, so yeah, the only failing thing is in the egg now. So let's fix that and then continue working on the toast. int.int and int.source. Sure, we can do that. Yeah, let's call this string. Nice. And this should be does each egg need that? Yeah, I think so. Yeah. And I think you should yeah, you should put do we want I'm not sure what to do here. I think that's like, where do you even need this? Maybe when we want to attribute the execution later on, for example. We want to show more errors. So I think that's safe for structs. The ampersand for structs. It's not just a slice of that. No, it's a toast struct. Simple. Ampersand. Yeah, I think the source is enough, but you know, and the fields, which is a slice of toast field, and this right here is toast struct. Beautiful. Yeah, toast struct with the fields being that and the ampersand being the
the result of calling consume this is that. Oh. Yeah, I guess that add bacon.source. Cool. So then, oh yeah, you can't iterate over a toast struct, but you can iterate over the struct fields. Oh, that's actually useful, readable, informative code. It is not a variable. No, toast has, the struct has an ampersand, and you could take the source of that. Oh. Yeah, like this. Nice. Ooh. Okay, the question is, where do we want to... Yeah, I think the member source, right? Yeah. Let's just do member.name.source. Like if there's an error, because this is not a struct or it doesn't contain this field or something, we want to show that, we want to underline the member name. Okay, symbol. Yeah, the symbol has a source. Like this. And the switch. I think we'll do something similar to the struct. Let's say the switch contains, show the condition, then the percent, and the cases. And when creating a switch, in here, we also create the percent. Where does the percent come from? Well, from here. Beautiful. And then we can just say that. Okay, for a name, we load up the name string. If that doesn't work, we have the name source to show the error. You know, this is really good. Rather than having this generic solution that underlines entire AST nodes, you know, like in Rust, that really bothers me, that it sometimes just colors like this red if a type mismatches. Yeah, like if this case returns something else, all of this is just red, for example. And that isn't helpful. For errors, you want to pinpoint them to some local thing, I think. Like underline this, for example, or this case keyword or something. Yeah. Right, the lambda, I mean, we can only make the backslash is there, you know, pretty obvious. Yeah, toast lambda has a backslash. Look at that. Yeah.
Yeah. Cool. Yeah. Nice. If something about the lambda is wrong, just underline the backslash. That's fine. Yeah, here switch on the receiver. I know. Well, okay. That is fine. And this is, oh, it's a call. Well, ew. Calls are kind of difficult, actually. Yeah, they are kind of difficult. Because what do we put in here, you know? You know what I think? I think in this case we actually want to move this body.push inside of the switch. Because depending on what it is, we want to do something different. Yeah, that makes sense. If it's a name, then or is it something different? Maybe the call receiver, hang on, that is a kind, toast kind or something. We could say, hey, call up receiver.source, source being a function that then calculates the source on demand. I like that. Yeah, we have all these right things, and then the source of toast expression is the source, and we just switch on the expression. It's a string, it's a string source. If it's a struct, oh, now that's interesting, it's the struct dot ampersand to the source up until the struct field. If struct fields get last, maybe. If there is some last field, then that field source, calling that recursively. Otherwise, just the ampersand again. For a member, well, easy, and member of source to member.name source. For a symbol, it's just the symbol source. For a switch, kind of more difficult, similar to the struct. We take the percent and we take the variance. Yeah, the last variant basically. But hang on, the switch variants, they are map entries. So this should be the value of that, like the body, yeah. For body, well, the question is, what if the body is empty? Do we want to allow that even? I'm not sure. I'm not sure. An empty body. I don't know. Okay, for name, it's just the source. For a lambda, it's just the lambda. What is the backslash source? Up until the lambda body source. For call, it's just the call. What's it called? Is it called receiver? Gotta change that. Until the last argument. And there definitely is one. Yeah. Var name until the var value source. Boom. So we don't have to save all of these sources. We just, compute them on demand. I think it's even more efficient. Yeah. Because we don't create all of these and we don't bloat up the tree. The tree is like a nice compact format. Not really. It's allocated all over the place, but in theory it could be. Okay, let's just see if this works. It doesn't, okay. Oh, because of some internal thing in the standard library. Well, of course, that's the way it is. Last maybe in the memory module. Let's fix that quickly. Standard lib mem. Hang on. 29. Yeah. That's just that. Wonderful. Okay, and for the fields, true, fields should have a value. We take the source of the field value. Yeah, for the variance, oh yeah, a switch contains cases, that is true. And we just take the case value source, perfect. A value is not a field on toast case, it only contains these fields, symbol, params, and body. And value is not a field, toast case. Yeah, that's the body, I guess. Beautiful. And for calls, yeah. We call ourselves recursively Wonderful. There's not a variant because the value can be anything, and the source is that. Yeah. I think here we can just say body dot first. And bodies are not allowed to be empty. We should check that and like make sure that we never create empty bodies. Okay, more egg problems, sure. 4, 3, 5. Define, guess what? The name is probably, yeah. Okay. Does this compile? Okay. It does actually compile. Beautiful. I mean, we already did quite a lot, you know. We refactored the source to be in the leaf nodes. Boom. Remove this. We should still do this. But not now, you know, it's when we actually want to implement formatting. Which is not the highest priority right now. This is going over the 80 column limit. You know, let's just commit this for now. Formatting, beautiful. I'm wondering, did this? Yeah, the toast. It definitely got longer, I think. Maybe. In some case, I mean, you know, I don't know. Lots of little changes. Well, many of them simplify the code. So, move source into toast leaves. Yeah. Beautiful. Yeah. Next up, let's just move downwards, you know, through this file and refactor things. Yeah, I think I want to change that. I want to call converting bacon into toast. I also want to call that parsing. Maybe let's add like a little description. The parser walks through a string from beginning to end. Yeah. The parser walks through a string from start to end. Yeah, it maintains a what does it maintain? It maintains a cursor to do that. But you kind of see that, you know. Well, still, parsing is important. This is more like a declarative thing. You know, this is the toast. This is what it does. This is what it looks like. And then, after all that, we can come to the parsing part. Nice. Where we can Is this actually used? From until cursor. No, it's not used. It has a weird sounding name, not a nice API surface. Yeah. Source of rest. Is that used? That is used a lot. Okay. Crazy. Okay. Yeah. Hang on, consume. Here we don't use the result. Here we don't use the result. Like, okay, let's not have consume white space, but only consume. Yeah, parenthesize expression, we just don't use that. Okay, the dot, we also don't use the source of that. Or the pipe. Or the equal sign. Or some weird, oh, I see, yeah, lambda things, type atoms. Yeah, parser.consume equal sign. Parser.consume that. Yeah, okay. Yeah, I think it feels more natural if we just actually return a string, you know. Consume. Consume with a char or consume with a prefix? Oh, hang on, do they actually like do different things? Consume white space. Here we save the start, okay, I mean, sure. Then we'll just go over the chars and check is the current equal to the char. If not, then we reset the cursor to the start, makes sense, and we say none. Otherwise we say parser.advance. Yeah. And this can just be source of, and then, and this is not even correct. Should be plus the string length of something. Alright, let's merge these. Let's merge these into one that accepts a string and returns a string and source, simplifying the code. Yeah. Start is this, and then here, end is parser cursor, source of, start to end. Look at how clear that is. And not just the source, but also the prefix space. Like this. Nice. Simplifies lots of things. Then in here, I'll make sure this is more like that. Oh, hang on, like that. But we can, just do that. Start quote, consume that. Oh, that is even more, like this was not correct. Because this also consumes white space, and the white space would have been included in the error message if there was something wrong. So, yeah. Okay, so start quote source. Dot advance. And this could, for example, end quote is this at parser the source of end plus 1. We don't need that. Here we can just say start quote dot source to end quote dot source. Crazy. Yeah, we don't really need this, to be honest. We could just say end quote underscore source, but this is like, I mean, why? Yeah, I like this. This feels cleaner, you know. Okay. First, use site fixed, and also like fix bugs. Yeah. Oh, yeah, this is some parent, and then we have parent.source down there. Beautiful. Yeah, parser consume dot. Wonderful. Parser.consume pipe. Parser.consume equal sign. Let's just call this equal sign. Nice. Equals, yeah, equal sign, equal. And I think parent.source is more, feels better than just parent underscore source. Feels more like this actually has more semantic. It's more like one object, one thing, one coherent whole that you can think about. The parent source is more like a intermediate value or something. Okay, equal sign. Sure. And this, oh no, this is just the backslash. Look at that. What? And this is the colon, which means this will be colon dot source. Oh yeah, and this is the colon, like this. Parser dot consume, and equals sign. That's just equals. Call it equal sign, you know. Wonderful. Equal sign. And this is equal sign dot source. Beautiful.
equal sign. Okay, yeah, that seems to work. Let's commit more things. Consume, make consume, return string and source. Nice. Then reordering these functions. You know, up here we have like a very nice rigid ordering. We have first like the general things, you know, the entire toast and the definitions, and then you have the type definitions and the toast types and all type related things, and then you have the functions and the expressions. And down here it's just all over the place, because sometimes I think first I have the parser methods like parse type item, parse expression, and so on, and then down below I have the you know, to toast expression, to switch, and so on. And I think it makes, at the time I thought, hey, it makes sense to have the parser things in one place and the things that operate on an entire bacon in another place. But many expressions have two variants. So for example, I think structs. I'm actually not sure if we support single line structs, but it would make sense, you know, and would make sense for those two struct parsing functions to be near to each other. So I think I'm going to reorganize this so that we first have all of the functions that that maybe work on types, and then all of the functions that all of the parsing functions that work on expressions. Yeah. Does it make sense to name this line parser just to be more, you know, more explicit about that? I think so. Yeah, let's call it line parser. Why not? Compiles, okay. Good enough for me. Yeah. Okay, so I should maybe note in somewhere. Where's the parsing section here? Parsing. Parsing in Plum is very, parsing in Plum is interesting. Plum has a strictly indentation-based syntax. Some prefix symbols. Yeah, maybe let's say Plum is strictly indentation based and doesn't have closing units that can span multiple lines.
for example, multi-line parentheses are not allowed. Instead, parsing in Plum works on two different levels, blocks, lines. Yeah. Parsing in Plum is interesting. Plum is strictly annotation based. It doesn't have closing punctuation. Oh, and and language constructs that span multiple lines are guaranteed to not have closing punctuation. For example, multi-line parentheses are not allowed. And struct enum and enum, function and lambda definitions are all terminated based on the indentation. Yeah. And then works on two different levels. This two different granularities. Blocks. These refer to blocks of the bacon. They are organized based on annotation and span over lines. Yeah. The lines, let's put that on the same line. Lines within a line, there can be within a line. Blocks. Now, annotation based. Oh, the bacon. Annotation based units. See the bacon. For more info, lines, things within a single, some language constructs can only work as blocks. For example, switch. Some syntax constructs can only work on the block. Granularity. Yep. For example, switch. Some can only work on the line granularity. For example, some work on both. Such
calls or script creations. Okay, nice. I think this is a nice overview if you want to read the code, and also for me, you have to have this rough framework of what is even happening here. Okay. Yeah. Then we have the line parser. The line parser works with a string from start to end. And then there are several like helper functions for that. I mean, sure. Oh yeah, this is also worth a section. Most parsing functions return a result maybe where the different possibilities have the following meaning. If it's an okay of some t, value was successfully parsed. And yeah, okay if none. The parser didn't match.
Parser didn't match. Yeah, the parser doesn't. Yeah, the parser didn't match. And there's error of the parser matched, but the input contains an error that should be shown in the editor. Okay. Do we have examples for that? Want something? Yeah, this end of user input is weird. Something that has, I don't know, bad input. Yeah, parsing parenthesized things. I think we'll just do the inline, right? The toast expression. Hang on. Where is that? Parse type expression and so on. Parse type. Oh, that's this is it. I see. I mean, you know, we may want to factor this out into a nice small parse parenthesized. I think we do. Yeah. If parse parenthesized parser line parser result is a maybe toast expression and an error. And what it does is literally this. Consume this or return doesn't match, like none or like no match of toast expression. Otherwise, this is the parenthesis opening parent. Beautiful. Then we pass this. If not, then we show an error at the opening parenthesis. Also we have this, and then we have that. And we don't really use that. I think we might at some point, so I'm just going to leave that there. Oh yeah, this should be a function. Oh yeah, this is a parsed thingy. And then up here we can just say parser dot parse parenthesized. If that is some expression, and if that is some expression, then expression. Boom. Look at that. Like that looks even more cleaned up. Damn. This is super nice. Yeah, and yeah, I wanted to write a small example here. An example for parse parenthesized. So let's say the input is, let's say this. We also have a cursor and that. Let's say the input is first, a value was successfully passed. 4. Cursor before is, oh, there was almost here maybe. Cursor after is here, and this worked. That is pretty cool. Then a second example that doesn't, like there is not an opening parenthesis. For example, having full bar. Before the cursor is there, afterwards it's there. And the third example is this, where before the parser was there, afterwards doesn't matter, and it returns an error. Expected expression. Yeah, I think it actually like remains there. Should be shown in the editor. you should not rely on the cursor. You know, I did not like actively think about this actually, but it makes sense. Yeah, in this case, the cursor is just garbage, basically. Okay, I think this helps with understanding the code, you know. And then here we have all of the different language items. Like parse int, yeah. Parse string, beautiful. Parse identifier with these nice identifier chars. Yeah. A lowercase a non-uppercase identifier also allows punctuation. An uppercase identifier. Beautiful. Parses sure. Parses an expression that doesn't include white space, except in parentheses. Yeah. If parser parse parenthesized is some expression, then we have an expression. Else is parser parse int, parse string, parse name, parse symbol, else no match. Beautiful. Actually beautiful. Could even like this, I think should be another parser. Like parse oh, I don't even know. Parse member, probably. Parse suffix member, I don't know. Something like that. Okay, so this is self-documenting. Oh, hang on, so yeah, I think I'm gonna use, I'm gonna move this to up here, because this feels more fundamental, you know. It's not really, because it's used here. I think there is no such thing as being more fundamental than something else, really, but yeah. Okay, parse atom, and then maybe parse suffix member, you know. Takes a parser, sure, and returns a result. Hang on, but it also takes an existing expression. Yeah, which is a toast expression, and then it basically does this. Or return no match. And then we pass the name. Or we say, hey, expected the name of the field. And then in here we say, hey, we successfully passed the toast expression member. Can we put that? Yeah, we can put that on the same line. Nice. And pass suffix member. So then in here we can just say an expression is parser dot parse suffix member of that expression. That may fail, or if it doesn't match, then we just break. Boom. And in theory, we could also like do or, you know, parse suffix something else, and basically parse more suffix things there. That is super neat. That is amazing. Okay. Okay, yeah, we can even it's getting crazier and crazier. Okay, loop expression. This is clean code. Damn. I mean, the parse atom here, it was so long and so many different levels of notation and detail. And now that all of these parser functions are factored out, it's nice. Hang, we don't even need, yeah, we don't use the star. Nice. Nice. Well, yeah. Okay. And because this is a suffix parser, it just takes the expression. That's super elegant. Then here parses an expression that doesn't contain pipes. Yeah, that may contain white space, but doesn't contain pipes, except in parentheses. Yeah. Puzzle lambda, why was that here? I think lambda should have been up here, maybe? No, it should have been even more down here, I think. Yeah, I don't know. For now, just refactoring. Yeah, single line lambdas would be nice to have, but not crucial. So the unpiped expression parses an atom, and then it passes arguments. If they are not empty, then we know that we have a call. Parses unpiped. Yeah, let's just leave that for now. I think that's fine. And here we say parse expression. Parses an expression including include white space and pipes. Okay. So first we parse an unpiped expression, and then if there's a pipe, then we parse another unpiped expression, and then we have piped call. Yeah, sure. What does piped call do? Yeah, before I check that out. Oh, hang on. I was kind of thinking this was in the loop, but actually it's like completely separate. So yeah, let's maybe add parse suffix pipe, maybe. Sure. parse suffix pipe. Yeah, takes a line parser and an expression and then a pipe. Yeah, basically this. Just does this. If there is no pipe, then we just return no match of this toast expression. Otherwise, we say we pipe into this other unpiped expression that we parse. Yeah, and in the end we return a piped call. Parse suffix pipe. And then in here we can just say no expression is parser dot parse suffix pipe of this expression or break. Simple. And like actually like very parallel to what we do up here. You know, first have some expression and then try to parse suffixes. Yeah, this is also looks like a suffix, but it is kind of special. Yeah. So if there is an expression after that, then we create a variable. Makes sense, I think. Oh, yeah, create var, takes the equal sign, source. I think it would be nicer if that would just take the equal sign. Because why not? Sure, it's a bit more info that you give to it, but it's more like a comprehensive unit of data. Yeah, just stick the equal sign, that's it. Okay, then parse unpiped expression. Yeah, parse this. Okay. Yeah, I guess. The difference is that if this doesn't work, then we just reset the cursor. Because after, no, we don't need this. We don't need this. No, we can just say equal sign. Dot source. Dot start. Oh, hang on. No, never mind. Yeah. Because the source is already translated into global. The global offset. Yeah. But we can do this. Yeah. That's at least a bit saner, I think. Okay, so if we consume an equal sign, then we try to parse an expression. Okay. Right, single line lambda, again, something that would make sense. Parse suffix pipe, we have that here. Yeah, lambda would probably be moved somewhere up, but I'm not sure. And then, okay, now we're at the type level. Do we want to do that? I think, no, let's, let's first have the type level and then the expression level, you know. So actually I think we will do this before parsing ints even. We just have parse type atom. I mean, this looks like yeah, okay. It relies on these identifier things, which makes kind of sense, I guess. Okay, so we have these. Then type atom. Yeah, let's break that up into smaller functions. Parse type. Yeah. For expressions, it parenthesized. I think we want to duplicate these functions actually. From, only write it once, this try principle, don't repeat yourself. It seems weird, but really they don't have a semantic connection. The name of type, sure, it's uppercase, but that's not really a symbol. And type variables like this, they are not really names in the sense of function and expression names. Because for example, maybe we don't want to allow plus as a type variable. I think that's actually that actually makes sense. We want type variables to be always lowercase. So semantically it's not a name, and it actually differs. But the symbol also is semantically something different, even though it has the exact same code inside. So I'm gonna copy that down here. Yeah. And these up here, they will be renamed to parse type name, and this will be parse type variable. Parses a lowercase identifier. Parses an uppercase identifier. No punctuation anywhere. This just needs to be uppercase, and this needs to be lowercase. And also, I think I'm gonna introduce like sections in here. Type, like parsing types. Yeah. And even though you might not think of it, type aliases like list t equals I don't even know, to be honest. Equals int like I don't know, foo t equals map t string. Plum has structural typing. Even though you might think, even though you usually don't think about it that way, type definitions like really behave like function calls. Like generic types. Types with type variables. Like foo t really behave like function calls. I don't know. They call the definition of foo. With the argument int. And you use generic types. Usage is like really behaves like a function call. For example, list int calls the definition of list with the argument int. So don't be confused if you see type variables and type calls here. Okay, parse type atom. Parse parenthesized type just returns something, and what it does is basically does this, right? So the parser needs to have this, otherwise it's gonna return, no, I couldn't parse anything. Otherwise it's gonna parse the type. Parser's not, yeah. Of course, we need parser. Or return no match. Expected expression, expected type after parentheses. Opening parent.source. Beautiful. And then we consume the closing parentheses or do something like this. Beautiful. Yeah, let's just save that as well. Swelled. And also move that up here. similar to how we did that in the expressions. And then in here we can just say parse parenthesized type. My voice is giving out. Well, if that is some expression, then we return that. Yeah, let me make some more tea and then continue. Okay, I have tea. That is super warm, but smells so good. Yeah, parse parenthesized type. If that is some type, why is this underlined? Oh, right. Yeah, because this can also fail. Then we want to return the parsed expression. Perfect. And then we can remove this. Yeah, this, I'm going to rename that from parse symbol to parse type name. Yeah, that makes sense, I think. Yeah, maybe, yeah, I don't know. At some point it probably makes sense to have something for built-in types, you know, but for now I think that's totally fine. Okay, toasttype.call. Yeah, name and args. Basically, yeah, I think that's totally fine here. I parse atom without yeah, that's correct. And then we have this much more readable. You know, you have this, you have this, you have this. Crazy. Oh wait. Can we even like do stuff like this? Now, if this is an expression, then expression. Else if the type name is some name, yeah, then this. Yeah, still a win, I would say. Else, if this is true, then we just have this type variable else in the mesh. Yeah, I think that's cool. No, then again, I'm not. No, I'm not sure. I'm not sure about that. No, let's maybe. I think this is totally fine. Yeah. With early returns. Yeah, sure. You know, for the expressions, I kind of like this. This is cool. But here we also want to do something afterwards with the expression. For the type, we don't, so yeah. And this is so short that we have these parallel structures. For the type, it's a bit more, a bit more typing, a bit more writing code. Okay, so we have the type atom. This can probably, no, not really. Okay. And then we have this parse type expression. Yeah, we should also have a comment here. Parses a type without white space. That doesn't contain white space. except in parentheses. Beautiful. And yeah, this just parses a type. Parses a type that may contain white space. Cool. Then parse type expression. I mean, yeah, the first thing I'm realizing here is this is just lambda. Yeah, let's add a function for it. Parse lambda type. And that's basically this entire thing. And we can remove the indentation for that by having this guard thing. We consume a backslash, or, no, it doesn't work, or we return no match, no toast type to be found here. Yeah. And then we have the arguments. Yeah, where we pass these types or break. Then we have this arrow, and then the return type. Yeah, you can. So nice, so nice. Yeah, return type. Let's see. Yeah, the return, we don't need that here. And I think that's it, that's fine. Then parse type expression can instead just do parser.parse lambda type. If that is some type, then we can just return that. Oh yeah, this only contains OK and arrow as variants. And yeah, beautiful. So we try to parse a lambda type. Otherwise, we try to parse a symbol. And then we pass the arguments and result in a call. Perfect. And then we have parse type atom. Parse type atom. Yeah, that makes sense. Oh yes, that makes sense. Cool. Yeah, I like that. And then here we have, oh yeah, this is now expression level. So parsing types, and here we have parsing values. Oh, did we have a new line? Extra new line? Yeah, nice. Yeah, parsing values. Yeah, with types handled above. This part parses values.
those expressions on the value level. Yeah, and then we have these. This is all refactored. Parser suffix member, beautiful. Unpiped expressions. Nice tight loops. Yeah, this is kind of, I don't know. Yeah, create var, I'm not sure about that. And in general, like we have, I think we have some sort of create var is used, and piped call. These helper functions that create var. What does that actually do? Oh, okay. It just ensures that the left thing is a name, and that's it. I mean, I guess, yeah. I think we should do better than that. I think we should just parse. I think toast var should contain a left toast expression, and then in the egg we can ensure that that is a name. I think in the parser we want to be as lenient as possible, because later on we also want to use this for formatting. And for example, if we have a variable and on the left side it says uppercase foo or uppercase true or something even, yeah, we still want to format that, I think. Yeah, so I would tend towards towards not looking at the type here. Yeah, okay. So I think toast var should contain like a left toast expression and the equal sign, and that we need the equal sign in here so that we can report the errors later on if something goes wrong. But that means that things get simpler. We'll just take the left source thing, toast var. Yeah, I guess. I mean, if this is called left, this should really be called right. Yeah. And yeah, I know. Right dot source, and in here we just we just don't do that. We just, instead of calling create var, we just create the var. Crazy concept, I know. Yeah, but the left thing is the expression. We have the equal sign and the right thing is that. Nice. Cool. Yeah, to toast expression. Oh yeah, same create var. And here we just have toast var, with left being expression put on here, the equal sign, and right being this. And yeah, and the egg we also need to adjust how we use that. I'm already at the correct location here. Yeah, the name is var dot. Oh yeah, switch on that. Yeah. Oh, we can even say var left dot name or return, bad input. Variables have to be lowercase and just var dot equal sign dot source, or the left dot source. That's fine, I guess. Oh yeah, it's not like bad input or something, it's just an error. A by B error. Beautiful. Beautiful. And then here we take the var right side. And obviously this is just the name. Okay, I mean this is not, so much worse than before. And we have a central place where we can handle that, instead of having to call out to some check whether all is good and create a var function in here. I think this is, this is better. Okay, so we have these parsing things, and okay, now things get interesting.
Yeah. Int. Oh, yeah, see here we have something type level suddenly. And I think this should go to the other type things. Yeah, so let's do that. Up here we have parsing stuff in general. Yeah, then we have parsing types. These parse parenthesize type, parse lambda type, parse type expression, and then we do some more parsing of types. And the way we do that is by, well, I think first of all to toast. Because this is defined on a bacon and we have overloading, there won't be any name clashes with just two type. But really, this should be parse type, I think. Yeah, there's not really an expression or an atom or something, you know, because this is an entire bacon. On that level, like white space stuff that doesn't even factor in, it doesn't even make sense to think about that. Yeah, and you can see there is, yeah, that's a function. Right, and here I would say also call it parse types, maybe. Yeah, have types, and then for each bacon, I mean, yeah, sure, do bacon dot type. Nice. Okay. Yeah. I pass type defs as well. That's an important distinction, actually. Yeah. Pass type def. Makes sense. So up here, two toast types. Instead, parse types. In here, two toast type, parse type. And down here, parse type def. Okay. Parse types. Beautiful. Here, parse types. Noise, noise, noise. Okay. Then, what to do then? Yeah, basically factor out smaller functions from this, I think. Yeah. Like parse struct, for example, takes the bacon. And yeah, it turns out there is no single line version of parsing a struct. Kind of sad. What do? Well, we check bacon.line equals this, or return, hang on. No, this returns maybe. Yeah, maybe toast type. Yeah, no match of this toast type. Totally fine. And then we have the actual body, where this can be simplified to parsed call. Yeah, so we have fields. And for each child, yeah, we create a parser. We create a parser and we say things. Expect a field name. putting some white space in here, I guess. Name, 1 unit of code. Then the colon, sure. Then type being something. And then we push that to the fields. Okay. So here we have a type. And that type really just checks are the children empty? Yeah, then we expect to parse a type on that same line. And then we want to be done. After field type. Otherwise, yeah, we pass the children. Should only be 1 child. And then we say, hey, the fields can only have 1 child. Yeah. Okay. Parsing a struct. Oh, yeah, we can just say we don't have a toast struct type or something, right? Of course we don't. Yeah, okay, so then I guess this is fine. Just do it like this, and we can basically remove this part. Then the enum case. Oh yes, very similar to the struct, I think. Yeah, just call parse enum. Well, yeah, and it's basically this part. So bacon line should be this. Okay. And otherwise we pass variance. Beautiful. Of a toast enum type that was successfully parsed. And the error cases here, they can be simplified to be that input of toast type. And that will look very similar to the struct above, where we have first a parser, then the variant names. Actually, let's call this child. Yeah, because it's not yet a variant, you know. We pass that child into a variant. Yeah, the arguments, if there are no children, then it's just the rest of the list here. Pass type atom. I feel like I've seen this code a lot of times. Hang on. Okay, so I have definitely type atom. Yeah, here definitely pass type atom. Here as well.
Yeah, for call, that makes sense. What was this up here?
The arguments, like parameters to a lambda, arguments to a type call, payloads of an enum thing. I think it makes sense to do something about that. Okay, so also, hang on, this idea of I parse a type or I parse some types down here. Like either, you know, I parse my children and I make sure that the parser is empty, or that's down here. Either I parse my children and make sure the parser is empty, or I parse the rest of the line and then I make sure that my that the parser is done. Yeah, it is very, very similar. I think we can unify that. Yeah, but first we have parse atom. You know, let's also add parse atoms, plural, which just does this. Not a lot of stuff, you know, but yeah, let's see. Basically copy this, boom, down here. And go atoms, and then we return atoms.toSlice, and this maybe returns a slice of toast types, and in here it works. It can return an error. Yeah, perfect. Parse type atoms. Yeah, and also the arguments, we don't need to convert them to slices afterwards. We can just say parser.parse type atoms. Boom. Done. That is clean. I'm wondering, just for the error handling, I think I'm going to change my formatting for that, because it's very, you know, gotta do it like Lisp, like having the closing things be on the end of the line. We can still like separate, you know, with things with white space, and I think that looks a lot cleaner than having these basically do nothing lines here. Like this is dense but still like very readable, especially because errors are not really they don't really span multiple lines here. It's just always a single line. Yeah, like I won't change anything else, only errors. Yeah, like here for example. Okay. What's going on here? Args. All right. Yeah. What if there are no arguments? Hang on. Hang on. Parse type atoms. Yeah, it only returns an error. or some slices. It never returns maybe. It's just that. Okay, so really this should be okay of slice of post type and error. Yeah. Yeah, I like how this looks now. You really get this overview of, you know, backtick, arguments, arrow, return type, done. And this is, you know, for dense code is really, really good. I think not because, like, sure, reading inside of one thing like this might be a bit more complicated, but as I said, like the complexity limit of building an error is quite low. So this is not really complicated, but at the same time you get a better big picture overview of what a function does just by looking at the structure of the code. Yeah. Okay. Okay, parsing a struct. First thing, adjusting the errors here. I really want to do before and after comparison of the number of lines, to be honest. Yeah. Same for enum, where we first parse the name and then the arguments, which are just parse type atoms. Beautiful. Really, really beautiful. Yeah, or we do this multi-line thing. Okay. Yeah. Hang on, that was parse enum, which I think is like, now it's pretty compact here. This looks pretty cool. It can be cooler, but we'll get to that. Yeah, parse enum. If that is some enum, then we'll just return that. And can we? Yeah, it goes a little bit over the line limit, but I think I'm gonna make an exception here just because it's so nice. Yeah, otherwise we do this, which is now less indented. Otherwise we do this, create a parser. Now it's the same thing again. That's crazy. Okay, so we parse a type and then we make sure we're done. Okay, I guess. Yeah, if there are no children. Otherwise, if there are children, then we parse a symbol. Yeah, there should be nothing else there. want to drink more tea. Yeah, I think let's maybe look at some I know how to unify this. The question is, should I? Should I do that? Like, for example, I could say, you know, I don't know, let's take let's have some function that takes the children and a parser, and we basically say, hey, please parse children, or like parse children, I guess, and it just looks if the bacon has any children. If so, then it ensures that the parser is done and it parses the children, and otherwise it parses children on the same line and then makes sure that the parser is done. And both cases could return this args thing, and we could use that here, but also up here, because here we could say, hey, please parse children on my children and the parser, and then this assertion here, checking that the length equals 1, we could do that afterwards. So basically be like, oh, hang on. Here we parse a type expression, and here we only parse type atoms. Okay, yeah, no, okay, I'm gonna leave it like that, like this, then. Makes sense. And it's really like, I'm not sure if it's like, it feels less like accidentally being the same thing, you know? But I am gonna add a helper method for this additional garbage after stuff. So parser is done. Parsing is done. Ensure done. That should just return a result of nothing or an error. And really it just does parser is done or return error. Of an error, additional garbage on line with the parser rest or the source of rest or something. Yeah, exactly. Otherwise you just say everything's fine. Everything is okay. Parser.ensure at end. Oh yeah, nothing instance here. The default return value of blocks. Let's just look for garbage. Dang, 16 times. Well, ensure is at end. it's not as precise because I've mentioned the field name there, but I think that's fine. Yeah. Crazy. You know, this is the kind of thing where you think, dang, this is elegant, like really, really elegant. So many times. But it is, you know, I'm still happy that I copied the code, because finding these useful abstractions is something that is very difficult to do up front. And like I do have some experience programming, so it works out most of the time, but no, making these premature abstractions is dangerous. So I'd rather copy this a few times and later on refactor than do it the other way around. Okay. Yeah. Let's look at what we did. We have, hang on, we're already in the values. The types are so small now. Yeah, we have this nice parser struct thing. We have a nice enum parser. Like, honestly, this is so much shorter than before. Okay. Yeah, and here if children is empty, there are no children, then we just try to parse a type expression. Expected type. Hang on, no, not symbol. No, parse type name. Expected type name. Nice. Yeah, and then it says parse ensure is at end. We parse the children, and we have a call. Beautiful. Okay, parsing types. Yeah, parsing a type definition means we create a parser. We parse the name. We parse parameters. It's just this. We consume the equal sign. I'm sure. We have a type. The actual type. If we don't have any children, then that will just be that. Yeah. Oh. I mean, yeah. When we support comments, we will need to change this to something. Like first parsing the children and only then
you know, only then checking if the length is 0. And by the way, this is correct. Yeah. Okay. Very, very cool. Parsing types, then parsing values. We have parenthesized, atom, unpiped, expression, suffix pipe, lambda. Oh yeah, and this is where the types suddenly reappeared. But now we have this. I see. Yeah, let's call this parse expression. No, just parse. Oh. Hang on. Nope. Just parse is parse expression, I guess. Yeah. And let's do this bottom up like the others. At least kind of. They were kind of bottom up. Previous is a nice. Oh, that's a nice name for that. Yeah, not to toast struct. Let's just call it parse struct. Beautiful. No, not really beautiful, but okay. Okay, then the fields. They each have a name, which makes sense. They have a colon, which also makes sense. And they have a value. And if there is nothing coming afterwards, we pass a single expression. Otherwise, yeah, we pass the children to expressions, and only then check that the length is actually 1. Yeah, makes sense. And then we push that to the fields. Beautiful. Yeah, let's maybe call this not field, but child. Okay, nice. Okay, parsing a lambda means we create a parser. Consume a backslash. We pass parameters. And then an equal sign. Sure. Okay, and then the switch. Is that really so? Yeah, that is really long. Okay, yeah, we'll check percent line first of all, then the cases, and then we return that parsed thing. And inside each case we create a parser, we create a symbol, we pass parameters, we pass a colon, and then we have the body. Okay. Yeah, this is just parse struct. Oh no. Hang on. Really? Like, yeah, there is parse struct. Which looks fine. And then there is... Wait, what? Oh, there's the type. Well, true. Parse struct type would perhaps be the more fitting name. Yeah, but then it should also be parse enum type, which, I mean, sure. And then just parse type and parse lambda type is also called type, so yeah, parse struct type, parse enum type. Oh man. Yeah, that's fine. That's fine. Yeah, let's maybe call it S and E. Not perfect, but fair. Okay. Yeah, this can be condensed a bit. Beautiful. You see, this, for example, is something where the second line is not just a single thing. So I tend towards leaving that here. Mm-hmm. I mean, yeah. Yeah, pipe call is weird. Again, kind of weird that functions are just named toast fun, but types are named toast type def, you know. Here's the parse param, and that was used like so much further up. I'm gonna move that up to parse lambdas or whatever that was. Yeah. Beautiful. Oh yeah. Cool. Very, very cool. Yeah. Parse fun dev. Hang on, where is parse type dev? Yeah, maybe I'll move parse type dev downward. You know, parse types and everything. And then here we have now that we can parse types and values, we can parse, let's parse type definitions and function definitions. Yeah, I don't know. Okay. Beautiful. I really, really, really like that. Okay. Yeah, clean up parsing, I guess. Oh, yeah, hang on. Let's just check that things work out properly what they will. Because we didn't change the data. Yeah. Nice. Yeah. Clean up parsing. Removed. Yeah. Yeah, I'm just gonna check if the formatting of these is really consistent. Now, if I had a formatting this, I would use that. But because we don't have a formatter,
I think we can also put in the extra effort to make things look really nice. And if we need to manually format things anyway, then yeah. Yeah, let's just remove this for now. If at some point we will add that, we can still do that. Doesn't mean we need that code in here now. Yeah, we can clean that up as well. So we have comments. Not really, actually, not really. That's just the way it is. Yeah, that's what I thought. Okay, nice. Clean up parser. Cool. Next would be the egg. Yeah, I'm not sure if I'm gonna do that today, though. When we have multiple modules, I'm wondering how the egg is gonna look like. Because in the egg, like everything needs to be resolved, right? Like functions, types, for example, should only consist of the primitive types or other types. So they should be the final plum types. So that means that imports also need to be resolved at this point, and like basically module, importing a type from another module. We need to resolve that while building the egg already. I'm not sure if that is smart, to be honest, or if there's yeah, or if we need to, I don't know, keep more types around, maybe. Nah, I don't know. I don't know. Plus, I'm not sure if it was the right decision to move the closure, turning that into a function, into the yogurt. Because the yogurt, converting egg to yogurt is already pretty big, and we do all of the type solving and so on. And this transformation, I think it should be doable without having types, right? Just create a function with a name, closure at position this and this in that file, and instead in the place in the code only have I don't know, some sort of some sort of lambda. And we know which variables the function captures as well. We do know that. I'm not sure. I'm not sure. Yeah. Anyways, yeah. Do I want to refactor this now? No, I don't think so. Wait, what? Oh, this is not in the correct place, yeah. This should be in types. Type. Yeah. Some is a structural type, so some types don't have identities. I think that's fine. Cool. Yeah. Oh, also I think joining types. Sure. Yeah. Should rather be called unioning types. I should give a reason because in the hang on, where's the yogurt? Oh, somewhere we had a to do. Yeah. In this example, you can really see that the results are unioned while the parameters are intersectioned. So I think it makes sense to use the mathematical terms intersection and union in the long term, rather than join, which doesn't really tell you which of the operations it is. Yeah. Okay, so unioning types. Yeah. I do kind of want to write the intersection of types. That sounds actually fun. Yeah. Okay, but of course, now some things don't work. Probably in here. Yeah. Okay. That's not... That's not a lot of references. Okay. Ah, okay. Move command to correct place, and then rename type joining to type unioning. Beautiful. And then yeah, maybe I'll I'll do the intersection of types. Yeah, that seems kind of fun. Yeah. Is that completely separate with the unioning? Or do we need to keep the currently unioning and currently joining in one? Like, do we need to keep both of them? Wait, can recursive types go across function boundaries? What? I don't think so. Oh, maybe. I mean, I don't know. Type iter, is a function that takes iterating over t is basically a function that that accepts nothing. Interesting. And returns a let's write it like this. It returns either done, like either empty or more of a t and an iter t. Yeah, so in this case, the function actually refers to that. What? Oh, but that, hang on, that only makes sense in the return value, right? In parameters, it doesn't. Yeah, defining a function that, in order to call that, you need an instance of that same type. Basically means it can never be created. Yeah, so, oh, okay. I mean, I should catch that and print something nice, but interesting thing. Yeah, let's currently just do this separately, the intersection. Intersecting types. And multiple branches evaluate to lambdas. Oh, well, we don't support casting them yet, right? Yeah, maybe let's not do that. Let's not do that. I mean, this is super cool, you know? Like this. What? Yeah. Okay, so let's maybe work on something else that's like small, and it's pretty late already, so. Did I change anything? No. Okay. I think that's just write more code, right? In Plum. I think that's a nice finish. Yeah, does this compile the iter type? Expected type after parentheses. Interesting. Oh, do we not support single line enums? Maybe not. Maybe we don't. What? Interesting. I mean, yeah, sure, for now, let's just. We can do. but the lambda type doesn't support multi-line types, I think. Well, that's kind of a dilemma. Problem solved, I guess. Yeah, okay. Fine, for now, that's fine. Oh yeah. Yeah, one thing I wanted to do is I figured out why certain things are not working. So, for example, if we try to, I don't know, create a struct, foo is 5, bar is high, and we pipe that to build in type of and convert that to a German description. Oh yeah, the return type doesn't match what is claimed. That is true. But also, and perhaps more interestingly, yeah, we can see this. Oh yeah, this is the entire heap. I mean, I guess, okay. Yeah. Okay, sure. Yeah, this is the result. I should not print the entire heap, I guess. Save the plum. Nah, down here. Yeah. Lots of logging. Doesn't matter. Okay, so yeah, this works. The problem is it doesn't work if you have if for each field you also want to print its type. So here, for example, we say it's a struct, and the fields are, and then the fields. And the fields defined in here, they just print the name. And it would be kind of nice if they also printed, you know, the type maybe. So something like this. Field.type. Yeah, I should. Yeah, okay. I mean, this is actually like okay-ish readable. String interpolation would be nicer, but yeah. This doesn't work because now we call type info on type that's not type. And at first I was like, why? What's going on here? So here's the thing. Like everything should be comp time, right? Here we call to Deutsch on a struct containing an int and a string. That means here this branch will be evaluated, which means the fields will be converted to German, which means this will be evaluated with a comp time value, and this as well. And yeah, for the first field it's more, for the second it's this. Yeah, we should also print this in that case, but anyways. Yeah, the problem is where's that? Yeah, here when we call rest. I don't know that actually works. Yeah, what is the trace to that basically? We have a lot of matching things and well, okay, let's move that first. Matching. Yeah, this. Nope, let's not do that. And what else? Compiling body to yogurt. These lowercase things. No, please, please no. Yeah, looking for a function is also not super helpful. And neither is this. Okay. So, yeah, we compile built-in type of this. Okay, that's fine. We get a comp time thing. So we convert that, everything comp time, That's super nice. Yeah, this, I don't know. Okay, there we call type info on that. Hey, we're done compiling type info of that. True. So then we do the string concat thing, and we stringify the fields. So this list that contains this. And here I'm like, wait a minute. Oh, here already, like compiling, building concat strings with a runtime known string. Here, compiling plus with a runtime known string. Why? Oh, hang on, this is a recursive type. This is not. Okay, we're done compiling type info, which makes sense. Oh, yeah, name and args. You know what that is? That's not the fields. Those are variants. Because even though the type is comp time known, we want to figure out the common type in union the types of all branches. So we analyze this as well, which means we compile this for variance, which means we compile this, which means we analyze this, which means we compile 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 I think at some point we compile this again and things break, something like that. Yeah, but basically we need a way to, similar to what Zig does, by the way, to do a comp time switch, to say, hey, we don't want to figure out the common type of all branches and see if they match. We want this to happen at compile time. And first I was thinking, that is unfortunate, you know? I mean, it's cool that things can happen at compile time, and that you can force them to happen at compile time. But it's also kind of weird. So I thought, what if you could switch on a type directly, not call type info and then have an enum that you can switch on, but switch on a type. And that would basically be the same as currently calling type info, but the difference is that when you switch on an enum, all branches are evaluated and the types need to line up and everything. But if you switch on a type, then only the matching branch will be compiled. The others won't even be analyzed. I think then it's very obvious, like when you want to opt into this compile only one branch behavior, you can do that. But the default is still the same version, Yeah, I'm not sure if there are any any disadvantages to that, if there are any cases where you really want to switch on a value at compile time. And in later compiler stages, we can definitely constant fold more and so on. This is only for the observable things and observable types and so on, things that affect overloading, things that affect the analysis. When we're at the yogurt level, we can still do constant folding and specialized functions and do crazy stuff, but yeah. We just don't want to highlight that in the language itself, I think. Maybe. Yeah. So that's basically the question I'm kind of struggling with. Because, I mean, the only place where you really need comp time values is for types. Everything else, it doesn't really, like, you can't even observe whether that happens at compile time or runtime. But types, they matter. And just being able to generate a type that is not comp time known, I think should not be possible. And with type info it does, though, because type info is, type info, yeah. Wait. I mean, then again, difficult. This is difficult. Yeah. I don't know. If you really want something to happen only at compile time, okay, you know what? Okay, same thing to do, I think, is implement that for types. And if any cases come up where you really want to do something at compile time, where you need to switch on compile time, where some code cannot be analyzed and shouldn't be analyzed based on some runtime known value that is not a type, then I can still add that later. I think that's the same take. So let's do that. Let's say, hang on, we removed some prints. That is always nice. Yeah, no, not this. Yeah, we'll remove some debug prints. And in the yogurt, I think, yeah, in the yogurt, you know what I was just thinking, like, we could even say that no type, like if you have something of the type, that you know guaranteed that it is compile time known. Can we achieve that? It doesn't make sense to achieve that. Basically, the only way you can get a type is by calling type off on something. And that is always compile time known. Like, even if this is a runtime value, the resulting type is comp time known. But of course you can use that to do, I don't know, coin flip, like make a runtime type that is that takes, I don't know, a foo, which is an int, and it just checks, hey, does this foo equal 0? If yes, then I'm gonna call built-in type of for. Otherwise, I'm gonna call built-in type of type. Yeah, and suddenly you have types that depend on runtime values. Yeah. I mean, Zig kind of does it the same way. In Zig, you can't have types at compile time. At runtime, you know, types can only exist at compile time. So it's not really too restrictive to do that, I think. We could say that joining types doesn't work, or like, you know, when you try to join types, we check, like, we know those are comp time things because types are always comp time, and if they are the exact same type, then sure, this evaluates to that. But otherwise, yeah, these types, they can't be joined. That would be a same take, I think. Ooh, yeah, that means you can't have hang on. You can build a, I don't know, a list of types, for example. Put a type in that and then get that from the list. Damn it. Yeah, I don't know. But at least you're switching on types. I think that is worth exploring. So, how would that even work? I think, first of all, we will just remove the type info built in. Oh. Simple. Right, remove that here. And here. Perfect. And then we will just change the yogurt. Here we have all this logic, you know, for, hey, we call type info something. Let's just create a comp time value. Let's not do that. Let's instead, in the switch, do something similar. Like if we have a switch somewhere, where here, this seems, yes, we have condition, condition expression, condition type, condition variance. Yeah, you still need to handle all. Yeah, cases doesn't really. Okay, let's maybe do that in here. So we switch on condition type dot. Yeah, on the condition type. If it's an enum, we do what we usually do. If it's a type, yeah, then we can only, then we do stuff. Yeah, if it's an enum, let's just move all of that in there. Know all cases, find the common, add cast expressions when necessary. Yeah, and then build this switch. Like this. Beautiful. Beautiful. And yeah, this is not a variant because types, oh yeah, it's a primitive type. Oh, come on. Some type. Yeah, I don't know. I guess let's check if condition type is primitive. Type. No, and is nope. Then if type is type, then we do something. We do this. But then we can't easily do else in both cases. Oh man. Is type. We can switch on enums and types. Switching on enums happens at runtime, but at least we can't. Well, no. Switching on enums compiles all and casts the values to the common union type. Yeah, let's do like this. Yeah. Switching on types happens at comp time. And only the chosen branch is compiled. Okay. Is condition type is primitive. And if condition type is primitive type, then type equals type, else false. Oh man, yeah. If it's type, then boom, we have this. Does that make sense? Apparently not really. Oh, because it's just too much indented, I guess. Else if type, and condition type, was it? Yeah, condition type is enum, then do this. That seems same. Else yeah, else we return error, which just says, hey, can't switch on. Can't switch on condition type. Yeah. And the source is the switch dot percent. No, that doesn't exist here anymore, I'm afraid. Or does it? No. Oh, does it? I mean, this is an expression. Can we just say expression dot source or something? What? What? That is amazing. That is super amazing. Yeah, and if it's a type, then we get and we know this is we don't know that. We get the expression. Oh, we do that up here. Yeah, that's not comp time then. On type, that's not comp time. Perfect. Return error with expression of results. Beautiful. Okay. Otherwise, now we have the type. Yeah, and then we have the builder, which pushes this just pushes a comp time thing. Now we kind of need to merge that with this part. Yeah, we need to first make sure the variant is handled. So rather than doing this directly, oops, man. Yeah, we get the type, we switch on that, and then we say we somehow need to get the body. Yeah. Okay, I'm just gonna copy that to here, because why not? All variants are handled, that no extra variants are handled, and that the number of parameters of each case matches the variant args. Perfect. So we have the condition variance, which is not actually a thing, but we do have the type info. I think I'll keep the type info type. You know? Yeah, type info. Yeah, that's an enum dot unwrap. You switch on a type, but you don't handle types. Yeah, and it's very similar here. You switch on a type and you handle the non-existent forbidden type. And for each case, we basically check that the variance case, that the parameters and the arguments, they match. Okay. Yeah, so we know all types are handled, and like all of that works. Yeah, and then in here we just do that. We just check what's if it's a primitive type.
So here we have a symbol. Please evaluate to a value. Oh, I see. So this is the value, basically. Nice. Yeah, the value that these evaluate to. And then, using that value, what we do down here is we lower the cases. In our case, we only need to do that for one variant. So in here we can say, hey, the case is, the switch cases get value dot it's definitely a tag dot symbol dot key or something. I don't know. Something like this. Yeah, and then we have the parameters, which are yogurt params. And for each arg we do this. Yeah. And if the condition expression is comp time, which yes it is, definitely, we get the value. We know it's a tag. Yeah. Value dot kind dot tag. Okay, yeah, I think I can just not oh, this is not correct, actually. I think, yeah, this tag is a different type. Anyways, yeah, tuple seems fitting, I think. Just have a tuple of this and a list of, like an empty slice probably, of yogurt values, and same up here. Yeah, and this is just, you know, a tuple containing enum and something. Yeah, and then we can just say tuple.a. Yeah. Then we clear the params, and then this is what we actually want to do. We push the param to the case, and then we, this is comp time known. Yeah, and then we convert the case to yogurt on the builder. Perfect. Yeah, we don't need to put the body in here, we just say that's fine. Yeah. I think down here we kind of need to copy that. Yeah. But up here we don't. Okay, so I think this is pretty cool. Yeah, I'm not sure we have the body here. We say just builder.push with something. Here we don't really. I will just do that. No. Yeah, good body. Okay, so yeah, no, we need to copy that, similar to what we do down down here, if this is comp time known, we do this. Well, and now we have the value, we know the variant, we have the body, case body, and then, okay, yeah, we just push those to our real body. I guess that makes sense. Let's see if this works. Oh, this was empty already now. Oh, switch on type, that's not comp time. Okay.
Okay. That is interesting. Now let's look at compiling built-in type of. Done. Compiling to Deutsch with this type. True. Compiling to Deutsch of that type. Yeah, even if this is empty, you know. Yeah, okay, it's not that easy. It's not that easy. Like, even if this is just a comp time type with an empty list, what that means is that we choose this empty thing. Yeah, and then this right here will just be, yeah, we'll choose this, but we'll also try to analyze this. Yeah. Okay, no, I don't know how to do that. I will have to think more about that. But that is fine. That is fine. I guess in the meantime, like that's like a dead end, I think. Do I want to commit that? I'm not sure. Do I want to switch on only on types? Let's say no. Because apparently that's not enough. And yeah, I mean, you know, having a function like type info also makes for nice documentation and so on. Yeah, it makes things more consistent, but yeah, if that doesn't even solve the problem, then I guess let's just discard those changes. It was nice that I tried this out, to be honest, but yeah, doesn't solve our fundamental problem. What I can do though is look a bit at how functions may interact with the outside world. That's like a thing I wanted to do for some time. Basically, functions are pure. So functions can't, I don't know, read you a file or print something even. We can't do that right now. I think what we want is returning effects from functions. And that's kind of, to be honest, I think the Rock way, or like the Haskell way or something, is kind of weird. You know, they have this IO monad or task in Rock, and that just represents all IO operations. I want to do something a bit more fine-grained, I think. So let's see, task. Yeah, so tasks. Yeah. Yeah, tasks can do stuff like standard out dot print line or something, you know. And I think, okay, hang on. Just want to see. Yeah, task has two type parameters. The type of value it produces when it finishes running. And any errors that might happen when running it. Standard out.line has the type task, this thing, because it doesn't produce any values when it finishes. And there aren't any errors that can happen when it runs. I mean, yeah, that makes sense. That also makes sense. Yeah, okay. And you have error handling? I mean, sure, but how does that work under the hood, you know? I mean, that makes, like, the syntax here makes total sense, I think. Yeah, creates a task which runs one task and then runs a second task which can use the output of the first task. Yeah. But what is a task? You know, can I just rock standard lib? Yeah. I guess. I'm not sure. Rock. Is it in here? Maybe. Crates? Not really, but sounds like Rust stuff. Hang on, I'm gonna Google this. I think Google is better in this kind of thing. But maybe not. Maybe not. Let's just look for standard lib, maybe. Standard lib function, solver, solve. And the organization, maybe. Platform stuff. Why is that so difficult? Nah, no. Is it called core or something? Is it linked on the website, maybe? Docs, I guess. Built-ins. Oh. Oh. A task represents an effect, yeah. Completes with done. Maybe at some point we'll need that. For now, I think I just want the main function to return an enum of what should happen. So basically, like, our result is already taken. You know what, let's name it task. Why not? So the program can say, please print something. Here's a string, and here is the rest of my code, basically. Like a closure, you know, something that takes nothing and returns another task. Or it can say exit, like done or something, you know. Now let's say exit. Now this should be able to return a task. Oops. Which means I think this should be able to return, for example, print hello world, and a closure that takes nothing and returns exit. Does this compile? No. Oh, yeah, an example of a task, of a lambda that, where types are recursive over the lambda boundary. Oh, okay. I mean, that makes sense, I guess. I think I'm not going to do that today. No. I've done a lot of programming already, so that is the challenge for next time. Yeah, I mean, we did a lot of stuff. Closures are working. Sorry, lambdas. And lots and lots and lots of refactoring. Like, the parser is now really, really nice. Yeah. Types called unions now. And we tried changing the switch so that it works on types as well as enums. But that doesn't solve our problem, so yeah, I need to think of something else. One idea which I also had was basically only, not monomorphizing functions based on the expressions, on the parameters, which are like this, you know, where each parameter is either runtime known or comptime known. So for example, if you have a function add, then I don't want to specialize that for int and 5. I don't know. But only specialize functions if all of the values are known at compile time. Like only, it either have all values runtime values or all values comptime values. Nothing in between. And that would make the language kind of less powerful in some scenarios. So for example, no, I don't even have that. Some sort of parse function, you know, which takes I don't even know. Takes a type. That takes some JSON maybe and a type, a target type, and it returns a result of that target type, and I don't know, some error, you know. Basically, you wouldn't build something like this, but instead build like something like this. You know, you can build JSON parser for a target type, and then that returns you a function that maps JSON to that target type. Like this is equivalent in its functionality to that. But I think this is more sane because we don't have this blow up of functions. Like, I don't know, if you have some brainfuck interpreter which takes a program and has an instruction pointer and a data pointer or something, and memory, and you know, stuff like that. Currently, if you call this with some brainfuck program, which is known at comp time, and instruction pointer 0 starting there, you know, and data pointer 0 starting there, and here you have your, I don't know, tape, which is a list of bytes or something like that. Currently, this would just explode. Like, it would be cool if it would basically generate a different function for each instruction pointer. And in those functions, you have a comp time instruction pointer, so get the corresponding character from the program and you know, fetch that, switch on that, and then do something. And like that, this fetching and decoding of the program, it happens at compile time, but that these are not like partially evaluated, that we don't have a function for DP and like, okay, example, brainfuck program like this. I think this just loops forever and it moves the data pointer 1 point to the right and then increases that. If you call that, if you call this, then the compilation won't terminate, because because you know the data pointer will just increase and increase and increase, and the compiler will compile this function for a comp time known DP of 500 and then 501 and so on. And if you have something else, like only run, I don't know, this many steps, you know, run this many steps in it, and this would basically be counted down. And but then you have a function, I don't know, brainfuck program, and you want to ask the user, hey, please, here's this brainfuck program. How long do you want to run this for? And basically this right here is only known at runtime. Then you will basically have the situation where DP is comp time known, and you will have some sort of if in there, a switch, you know. And if this right here is 0, then we will just return. Otherwise, we will recursively call brainfuck with the same program, the same IP, and DP plus 1. If we are here right now. And even though dynamically this will not run forever, it will still analyze all of the, it will try to analyze all of the possible data space of all these individual parameters. And this can happen very easily, like very, very, very easily. Because, of course, there are some functions where some parameters like they depend on each other and they're comp time known even. But then how long this thing will run is only runtime known. And in that case, we can't even compile a function like that currently. So I think the saner thing to do would be to have some sort of brainfuck function that takes a program and an instruction pointer, maybe. And then it returns to you, I don't know, compile a brainfuck program or something. Or like, I don't know, brainfuck state, maybe. Or something, you know. Something that that's basically just a function that takes some sort of state that is just a function, turns to some sort of state that is like, let's call it compiled program, you know? And it takes a state and it produces a new state. And the instruction pointers in this program. And the state is only the data pointer and the tape. Maybe how many steps this runs, you know. But basically by choosing how you nest functions, you can also choose which of these functions will be evaluated at compile time and which will only be evaluated at runtime. So I think from from someone using this language, it is a lot more sane and gives you more control over when things get evaluated and which things explode and which don't. And at the same time, from the perspective of a language implementer, we wouldn't need all these. In the yogurt, we have a lot of these is something known at compile time. Like, hey, we call some sort of function. Let's look at the function. Let's compile the function. And of course, all of the arguments, we need to check if they are runtime known or compile time known, and then build up this parameter list, then compile the function for that, specialize the return type, sure. And then we need to check, are all of the arguments compile time known? If so, then I really just want to, well, insert this call because I may panic, but then just dig into the function body, which is weird, you know, and see, hey, what is the expression that the function returns? That should be a comp time expression. And then I'm going to push a comp time instruction for that. That's super weird. What I think would be nicer is if we just had, I don't know, some function in our compiler that basically says run this function with these values, these comp time values. And then you can see if the arguments of this function are comp time, then I just call this function and that's it. Simple. Yeah, that's basically the idea. Separate out the compile time stuff into a more explicit, more restricted set of the language. Again, future work. Nothing for today. Right. Yeah, I guess that's it. And see you next time.